workshop is being organized by the NSM Nodal Center for Training in HPC at IIT Goa, together with National Institute of Technology Arunachal Pradesh. So both IIT Goa and NIT Arunachal Pradesh are joint organizers of this workshop. The objective of this workshop is to give an introduction to the participants about high performance computing, uh, what it is, how they can conduct research, how they can conduct courses in their undergraduate or postgraduate programs, things like that. And also to give them an understanding of the National Supercomputing Mission. Accordingly, we have lined up a group of speakers with us today, which I will introduce in detail when they are ready for the talk. We have Mr. Ashish from CDAC, we have Mr. Bharat from Nvidia, we have Mr. Dr. Sudhakar Yogaraj from Mechanical Engineering IIT Goa as our co-hosts. In addition to that, I would like to thank Professor B.K. Mishra and Professor Sharma, directors of IIT Goa and NIT respectively, for sparing time to grace the inauguration of this workshop and also for encouraging their faculty members and students for participating in this. So with that, once again, I welcome everyone here, and I would request Professor B.K. Mishra to say a few words for our participants today.
Yeah, thank you, Sharad. Thank you very much. I'm glad that NIT Arunachal Pradesh and IIT Goa are doing this very important workshop under this Nodal Center for Supercomputing, and there is a lot to learn here, and we have been doing these activities quite regularly, and thanks to the help of Mr. Ashish Kuvelkar ji and entire CDAC team, those you have been hand-holding here. And we see people, those you had participated earlier, they had benefited quite a lot. And in today's day and time, where everybody talks about artificial intelligence and machine learning, there is no escape from high performance computing. Now, these are certain parallel processing tools. I hope you will be discussing here how to implement your scalar programs here to parallelize, and you should also be, I hope, discussing, as I see Sudhakar is also here. So Dr. Sudhakar Yogaraj is an expert in fluid mechanics, and it should give you some elementary problems to, or share his experience, how he's been dealing with high performance computing system here that we have put here. There are many issues, of course. I mean, saying HPC is not end of everything. Yeah, I think Sharad, my connectivity is a little bit poor here. Okay, so that's why. So anyway, you guys are coordinating, and I hope that it will be a very fruitful event here today. Okay, thank you very much, and I thank Director NIT Arunachal Pradesh, who's been so kind to be here. Okay, thank you very much. Thanks, sir.
Thank you, Mr. Mishra. I would also request Professor Mahanta, Director NIT Arunachal Pradesh, to share a few words.
Thank you, Sharad. Am I audible?
Yes, sir.
Yes.
Okay.
Yes, sir. Yes, sir.
Professor B.K. Mishraji, Director IIT Goa, organizer of this event, Dr. Sharad, IIT Goa, and Dr. Vanav Kumar from NIT Arunachal Pradesh, participants, faculty, colleagues, and students. Apart from that, all the dignitaries of CDAC, particularly Ashish Kuvelkar and from IIT Goa, Sudhakar, Yogaraj. Very well welcome to this one-day workshop scheduled and jointly by IIT Goa and NIT Arunachal Pradesh. It is my pleasure to be present here today because it is a high performance computing is taking a big step in recent time, particularly in the different areas. If you go for like electronics, computer architecture, system software, programming language, algorithm, as well as computational techniques, when it is said, high performance computing is always taking a role. The major areas, as I mentioned, some of the examples, maybe airflow over automobile or aeroplane, the molecular interaction while delivering drug, then thermal management of the devices, unsteady flow, which requires a lot of parallel processing and time. So all these, I think HPC plays a vital role, particularly CDAC is the nodal agency for us, which will be helping us for bringing more and more scientific community into this field. As I am also a part of IIT Guwahati, we have our own parallel processing machine. Earlier it was Garuda. Next version came up in 4 years' time. That is also there. So that way, high performance network is forming a good shape. As far as NITs are concerned, we do not have that kind of facility. I think these joint collaborations will definitely help the students and faculty members to go for and interconnecting this type of high performance computing. I welcome all of you again, and I hope this is not the end. After maybe this is just a one-day program, but a thorough learning is required. For that a 10-15 days program, maybe offline program may be constituted. That maybe with hands-on practices will be more helpful. So thank you all. Without taking much time, I think we should go ahead with this. Thank you.
Thank you, sir.
Thank you, Professor Mahanta, for your kind words. In fact, I would like to share here with all of you that indeed this is just the first starting step. This is a virtual workshop, but we are planning an in-person workshop at NIT Arunachal Pradesh in the next couple of months, and that would involve hands-on as well as lectures. And again, we will have our speakers from CDAC, Nvidia, IITs, and of course from the local NIT Arunachal Pradesh as well. So we are working on that, and we will definitely take it forward as a collaborative activity.
Thank you.
Sir, just a minute, sir. There was a bit of glitch, so I joined maybe 2 minutes late. So, sir, before we start, I just want to thank our director and director IIT Goa, sir, B.K. Mishra, sir. Hope he is there online. So my heartfelt thanks to Sharad, sir, and director, sir, B.K. Mishra, sir, and our director who is busy. Maybe you are all busy, very tight, and I was fearing that sir should join, and I'm really thankful for all of you. And I hope this goes on very well, and we take it forward. And as sir pointed out, we would like to grow along with other expertise, eminent institutions. So this is my heartfelt thanks, a small thanks to all of you, sir. Thank you, sir.
To Dr. Vanav Kumar. Okay, so we will move on to the first talk for the day. So this talk is titled Introduction to HPC Cluster and Programming Models and an Overview. So this talk is mainly to give the participants an idea of what is an HPC cluster in terms of hardware and how we go about using the cluster using some programming models. This talk will be given by Mr. Ashish Kuvelkar, who is a Senior Director in the HPC group at CDAC Pune. He is also the head of National Supercomputing Mission's Human Resource Development Group, and he is very closely involved with the 4 nodal centers in the country as of now, one at IIT Goa, another one at IIT Palakkad, the third one at IIT Madras, and the fourth one at IIT Kharagpur. He is very active in the HPC community in the country. He also serves on the program committee of Edu High PC, which is a conference dedicated to education of high performance computing systems and in related fields. And luckily this time it is being organized in Goa, so we will see each other. So thank you Ashish ji for sparing time on a Saturday and I welcome you. Please, the stage is all yours. The virtual stage is all yours.
Thank you. So am I audible?
Yes, you are.
Okay.
Yes, sir. Yes, sir.
Okay. So shall I start? Okay. All right. So good morning, and I'm happy that the Nodal Center at IIT Goa is organizing this workshop. And as we see, distance is not a bar. Like Goa is on the west coast, and Arunachal Pradesh is in the easternmost part of the country. And good to see that we are able to bridge this gap, and I am at Pune. So the title of my presentation is I will introduce you to high performance computing and talk a little bit about the programming models. Maybe more about this we will cover in the upcoming in-person workshop that we will have. So Sharadji, how much time do I have? My time is for till 11:20, is it? As per schedule?
You have about 45 minutes. So
okay, fine. So
you can continue up till 11:20 also. We started a little earlier, so it's fine.
Yeah, okay, sure. So this is the outline of my talk. We will begin with an introduction. Then we will see what are the basics of HPC, the foundations on which HPC runs. Then it would be good to see what are the components in a supercomputing system. That's the physical parts in it. And then we move over to the parallelization being the key thing in a high performance computing. What are the various paradigms that we use, and we end up with a summary. So let's begin with the introduction. So this is a very old 75-year-old computer, the first one that was acknowledged to be available publicly or known to be one of the earliest computers. So that was called as ENIAC, which was used by the Department of Defense in the US. And you can see that it's quite big and all sorts of wires, and there it was based on vacuum tube, and it was used for calculating the angle for the missiles that the soldiers would use during World War, to set the angle such that depending upon various parameters. So it was basically a system that was used for doing a lot of calculations. Then we see these speeds that this starting with this 1940s, the speeds that the computers have been able to achieve. And if you notice here, let me just, okay, yeah. So if you see here, this green line here indicates the operations per second, whereas the blue line that you see here is the floating point operations per second. So we started off with you can say modest hundreds of calculations that the earliest computers could do, and as the blue line indicates, they were integer operations, and this all these systems were built using vacuum tubes. And this gap here that you see is the time when transistors were invented, and when we started getting transistor based digital circuit designs, and large scale integration, medium scale integration based ICs, uh, we started using computers for doing floating point operations in a second. And today, what we started modestly as something like 10 raised to 5 operations per second in the 60s, now we have reached 10 raised to 18, that is exaflop. That is the first publicly acknowledged exaflop supercomputer is installed at ORNL, that is in US, and that's by Department of Energy. So the take home message is we started modestly with integer arithmetic, but now HPC is used for doing highly accurate mathematical operations, and they are being done at the rate of, I mean, the top supercomputer can do it at the rate of 10 to the power 18 floating point operations in a second. That's quite a phenomenal speed. So I use the word flops. So what does it mean, and what is its significance? So that is the measure of performance. That is the compute power. How much computation that a computer can do is measured in normal in terms of operations per second. But when we are looking at supercomputers, we are trying to see how many floating point operations it can do. And as I mentioned here, we started with modest flops, then we had mega flops, teraflops. So many of these computers today, they are in the range of petaflops. Like the top supercomputer in India is about 6.4 petaflops compute power that it has, and it's called Paramsiddhi AI, that's installed at CDAC Pune. And as I mentioned, 10 to the power 18 is where the top supercomputer is today. And how does we know which are the best supercomputers in the world? So there is a benchmark that is written by Jack Dongara and his team, which is called as High Performance Linpack, or HPL. So every supercomputer has got a theoretical peak compute power depending upon what clock speed the CPUs are running at, how many cores the CPU has, how many such CPUs are there in the system. If you take the cumulative sum of the compute power of all these CPUs, we get the peak compute power. So peak is theoretical. That is the maximum it can do. Whereas what HPL does is it mimics some of the real life problems in terms of some algorithms in the CFD, some algorithms used in the bioinformatics, and it solves some matrices. So it's a combination of various algorithms, and it finds out while running a real life program how much out of this peak it can the supercomputer actually deliver, because you cannot have all the cores of the CPU all the time performing floating point operations, because there would be a program would have some calculations, it would have comparisons, it would have jumps, all these kind of instructions would be there in a real life program. So when you are running a real life program like a benchmark like this HPL, how much is the performance that the particular computer delivers? That is found out by running the HPL. So let's say Paramsiddhi AI is installed at CDAC. It was done about 3 years ago. Once the installation is complete, the CDAC system administration team would run this HPL, and at the end it would run for a few hours, maybe tens of hours, depending upon how big the system is. And at the end of it, it will give a number, and that number is submitted to this top 500 website which is run or managed by Jack Dongara and his team. And you get a chart like this if you plot what has been the performance over the year. So like this list started sometime in the mid 90s, and this triangle, the orange triangle here, shows what is the performance of the top computer in that list. So this list is published twice a year. It's published in the month of June and it is published in the month of November, which coincides respectively with International Supercomputing Conference ISC at which is held at Germany, and in US the Supercomputing Conference is held in the month of November. So during these conferences these lists are published, and you can see that how the computing power of the supercomputers have increased over the years, and in the year 2022, I think that is not captured here, the exaflop has been reached. So current supercomputer, top supercomputer is Frontier, which gave the result of 1.102 exaflop, that is 1102 petaflops when HPL was run. So Department of Energy owns this. They have installed it at Oak Ridge National Laboratory. Another take-home message for us is here. So this is the number 1 rank system. Then these blue squares are the number 500th. So if you take a particular list, let's say at 1995, the top supercomputer would have been at something, let's say 200 gigaflops, and the bottommost, the 500th one, would be about 1 gigaflops. So this is the range in which, and this, as you see, the range keeps changing because better and better supercomputers are being installed every year. So one of the take-home messages from this is that you look at this, what was the top supercomputer in the year, let's say 1994, it was just above 100 gigaflops. And if you go to the year 2002, you will find that it had moved to rank number 500. And in 2004, it was not at all in the list. So yesterday's supercomputers do not remain supercomputers of today. So it's a moving list. The target is moving. And for that matter, let's say if you take a supercomputer of say 10 or 12 years ago, that will have less compute power than the mobile phone in your pocket. So whatever good enhancements that are made to reach the top speed in the supercomputers, those kind of techniques eventually appear in the processors that we use in our day-to-day use. So this is one of the take-home messages for us, that the speeds of supercomputers are increasing every day. So now let us try and understand how and where are these supercomputers used. So to set the context, let us see how the science was done in a traditional way. So first thing that we would do, the scientist would do, is tell a theory saying that the things will work in this fashion, or they will give some equations to support their theory, and that theory is then observed through some experiments, and once they are observed through some experiments and it can be done in a repetitive manner, then we say that it is science. That you theorize it, you put forth the theory, prove it through experiments, and it can be done in a repeated manner, then we will say that no, this is not fluke, this has not happened for just one time, it can be done repeatedly. So that is what we say, that is a science. That's the traditional way. And the basis of science, I mean, all of this is done through mathematics, as is been aptly put by Galileo when he said that mathematics is the alphabet with which God has written the universe, which means that any phenomena that you see on Earth, beyond Earth, in the universe, there is a mathematical basis through which, like even starting with Newton, he observed a phenomena of apple falling down the tree on his head, and then he put forth a theory, and then he put forth, then he proved that theory through experiments, and thus then he had his equations, Newton's equations, which through experiments it could be proved, and the basis of that was mathematics. So whether it is physics, chemistry, biology, or any other science, you will find that mathematics plays a big role in it. And computers are good at doing mathematics, and we saw that earlier they were be able to do mathematical operations at integer level, but today they have graduated, they have migrated to even better for better accuracy using floating point operations. So now the modern way science is done in a slightly different way. The basis is same, that you have a theory, you do experiments, but you have another tool with you, that is computations. So when you have the computations, you need not directly go towards experiments, but your experiments can be aided through computation. And the difference between doing physical experiments and computation is that computations can be done much faster, whereas experiments may take time. That's where now computers come in, because your science is now being aided by computation. So we have science, which is based on mathematics, and we put science, mathematics, and computation together to form the basis of computer science. When all of these three come together, we have what is called as computational science. Science not just aided by experiments, not just theoretical science, but that theory can be proved through computation. And of course, physical experiments is the last stage, wherein the number of experiments can be reduced by making use of computers to simulate some of the experiments that you otherwise would have done, maybe in the area of physics or chemistry or any such allied science. So that is where HPC comes in. And when you have computation and you want to do many of such computations, which we call it as high performance computing, that's used in various aspects of our life, including our day-to-day life. So here are some compelling reasons where HPC needs to be used. In our day-to-day life, we find that it is being used for forecasting weather, and it's also used for giving early warnings of the coming storms or cyclones or tornadoes. So weather forecasting and early warning systems are closely related. Similarly, bioinformatics is playing a big role in improving healthcare, and HPC can be very easily used there. Similarly, it finds use in science as well as engineering. Two examples of science include finding new materials by investigating electronic structures and trying to find out their properties and the materials made out of that, how will they perform for a given application. Or other extreme on a bigger scale is exploring universe, how stars were formed, how gravitational waves are being transversing the universe, how they can be detected, and from them trying to find out, let's say, how the universe was born, what was the origin of Earth. All this can be investigated. They find very good practical applications in engineering, like as I said, mathematics is what the supercomputers are good at doing. So you can use it for simulation, and you can, before the product is manufactured, its properties and other things can be simulated on the computer, so that while you don't have to do too much of prototyping. You can directly go for a reduced design cycle and directly go for a few number of beta prototypes, and then by testing them you can then go for actual production. Similarly, in civil engineering, uh, you once a structure is designed, one can analyze it. Let's say if it happens to be in a seismic zone, how will the external forces going to affect it? Is it safe for humans to stay in? All that can be, or if you're building a bridge, whether the flow of water, the seismic conditions, all these external forces, if as and when they get applied, will the design or will the structure remain safe to use? So such things can be done by making use of high performance computing. So just to expand on that, not only it's used in forecasting, but these days it is being increasingly used for uh, air quality monitoring and as well as climate prediction. Similarly, in earth science, which is about understanding the physical properties of crust of earth and below the crust of earth. Similarly, for seismic exploration, water resources modeling, these are some of the applications that are used that uses HPC. Space science, as I already mentioned, in astronomy and astrophysics, you have telescopes which operate in optical as well as radio band. So data that is collected by them can be analyzed using high performance computing. I had mentioned above life sciences, so this is used for drug designing. Similarly, for designing personal medicines, you need genome sequencing. Then understanding the structure of DNA, you can be done using simulating how protein folding works. In science, another area where it's useful is in for nuclear power, as well as treatment of cancer can be done through nuclear radiations. So what would be the adequate amount of radiation that needs to be given? So that can be decided using these algorithms. And finally, as I mentioned earlier, in design of new material, then understanding the properties of semiconductor physics, microfabrication, all of these fall under the purview of nanoscience, and you have softwares that aid in doing this. Coming to engineering, in automobile engineering, it is widely used for simulating crash of automobiles. So the traditional way was build the car, design the car, build the car, crash maybe a dozen of those, and in between keep improving the designs. But this method is costly as well as time consuming. So you can simulate the crashes on the computer, and when you are satisfied it, build the prototype, crash the car and see that it exactly behaves as it was predicted by the design, and then you can do some tweaks and the car is ready to market. Similarly, while designing missiles and other objects that move through fluids, including ships, you can the aerodynamic simulations can help in designing the profile, designing the material that can withstand the heat that could be generated. And as I mentioned earlier, bridges, dams, etc. can be analyzed structurally before they are actually constructed. All right, so that was, I guess, a good way to get introduced as to what is the basis of HPC and where it is used. So now let's try and understand the principles on which the high performance computing works. Okay, so here being a academic institute, and I guess you may have some students, I thought we will start with the Flynn's taxonomy that the students of computer science would have studied in second year, where he had come out with 4 architectures. The first one was SISD, that is, you have a single processing unit which runs a single series of instructions, and each instruction has its own data. So single instructions working on a single stream of data. If you move towards the right, you have multiple processing unit. Each processing unit has got its own instruction. However, all the processing unit uses the same data. So you have multiple instruction but single data. Then comes the next one, that is single instruction but multiple data. So the multiple processing units use the same instruction. However, each one of them works on different set of data. So this is also called as vector processing. And the earliest supercomputers like Cray, they would work on this principle. And today, it's also used by the GPUs, the graphic processing unit. They are called as accelerators in high performance computing. And even some of the CPUs, the instructions can work, a single instruction can work on a longer length data, which is internally divided into multiple data units. And we have MIMD, that is we have multiple processing unit. Each processing unit has its own instruction and each processing unit has its own data. So that is MIMD. So supercomputing cluster is an example of MIMD, and we will discuss that in more detail because MIMD clusters is the most popular supercomputing architecture as of today. So just to recap, SISD is a sequential computer because it has only one processing unit, no parallelism, and it's not a parallel computer. SIMD, as I mentioned earlier, it's also called as a vector instruction. So there is a single instruction scene. So the instruction is, let's say, add, but instead of adding two numbers, you can add a set of numbers, which, let's say, 4 sets of numbers. So A1 is added to, let's say, B1, A2 is added to B2, like this. You can have 4 sets of numbers being added simultaneously. MISD, so this is just a theoretical one. You will rarely find being implemented except when you want to have some fault tolerance. MIMD is the one which is the most popular, and the clustering, as I'll explain later, is a kind of MIMD kind of architecture. Now the principle on which the supercomputing works is that you will use supercomputers only to solve large problems. You will not use them to solve small problems. For that you have your standard desktops. So when you have these large problems have to be divided into small ones. Then, because what will happen is small problems will run faster, large problems will take long time. Now that these small problems get over faster, the key comes from the fact that these small problems are solved concurrently. So this is very important, that the problem that you have should be possible for you to divide it into smaller problems. Not only smaller problems, they have to be solved concurrently. Then only you will reduce the time that it takes to run large problems. So we are trying to run large problems in lesser time. That's the principle, and the key there lies in having multiple computing element. So parallel processing is the basis on which high performance computing achieves higher compute power. The parallel tasks that you have made, the smaller tasks that we have made in the previous step, are each one of it is assigned to each of the processing element, which independently process the instructions and its corresponding data. So MIMD is one of the ways in which we can achieve this parallelism. Another term that is also commonly used is distributed computing. Here the concept is same as before. However, the multiple processing elements could be isolated, like through a local area network or any such thing, and they could be heterogeneous in nature, means the CPU and the operating systems could be different. But homogeneous ones are the ones that will give you a better performance, but heterogeneous may be used if you want to aggregate compute power or you want to reuse what you already have. So how does parallel computing manifest itself into supercomputing? So at the heart of HPC lies parallel computing and parallel processing, and the purpose is to put many compute elements together for running advanced application programs. As I mentioned earlier, for simple ones, your desktop can be used. Now, what is HPC good at? HPC is good at fast numerical simulation. So mathematics, floating point calculations. If you want to do that, then HPC is the technology of your use. Then modeling, we saw that if you want to model a DNA or if you want to model a solid that is moving through a liquid, these things need a lot of floating point operations to be done quickly. So they also are the good candidate to be used for HPC. Or if you have large amount of data, like a radio telescope or an optical telescope, it has gathered large amount of data and you want to find derive something out of it, then using mathematical equations, you will be able to do it. As I mentioned, just to repeat, if you have good amount of mathematical calculations or data processing or searching this kind of algorithms, then you should use HPC. So it will use the high compute power it has to execute a few applications very fast. So please remember that suppose you have an application that runs on a desktop and you say that I will run it on a supercomputer and it will run fast as it is. No, that is not the case, because the application that you are running on a desktop is most likely to be a serial code, and it's not that the supercomputers have got very high frequency of operation for the CPU. It is substantially good, but it is not a few orders high. So your program, the serial program running on a desktop, may not gain any advantage by running on the supercomputer because it is serial in nature. It cannot make use of parallel processing element. However, the program that has been inherently written in a parallel manner can run very fast. Now, what is the definition of the supercomputer? As I mentioned during our discussion on the list that I showed and the graph that showed the top supercomputers, we can now say that a supercomputer can be defined as among those computers that we have that performs at the currently highest speed. So that what currently is important, as I said, what are supercomputers of today are not going to remain supercomputers of tomorrow. Okay, so that is the definition of supercomputer. So now let's see what are the components in a supercomputing system. So we said that MIMD is the way to go, clusters is the way to go, and that forms the basis of a supercomputer. Like you have n number of compute nodes. You can have as low as 4 nodes, or you can have as big as 256 nodes, or you can have 10,000 nodes. So these nodes each will contain a computing element and it will have its own memory and other things. So these compute nodes are the ones that are going to be used in parallel. If you want to use them in parallel, then it is obvious that you need to connect them, all these nodes together, and that's done through a switch fabric like InfiniBand. So this switch, it not only connects all the compute nodes together, it also connects to storage, because your code and data is originally going to lie on a storage, and from there it will be brought to the compute nodes. The compute nodes will process it. While processing, they will generate intermediate data. Ideally, it will go in the RAM of that, but the data is so huge that it has to intermittently go to the storage, and that storage is implements what is called as a parallel file system. All of you would have used NFS or any other file system, that's NTFS, that's there on your hard disk. But the files there are, they can be opened by a single process for writing. Multiple processes can use it for reading, but writing is allowed only for one process. But here, parallel file system allows each of the node to work on a part of the file. Your file may be large in TBs, but each of the node is reading and writing, processing part of the file, and as a result, the parallel file system allows multiple processes running on multiple compute nodes to access parts, each process using one of the parts of the file which is implemented under parallel file system. So this is the heart of a supercomputer, but that's not enough. There are few more elements like the data that is coming from the parallel file system, which is uses rotating magnetic disk like SATA to be cached in SSDs. So these devices, these are like nodes that contain large amount of SSD storage. So SSDs, as you know, can read write faster than the magnetic drives. So the data that is served to these compute nodes is from the storage accelerated nodes. Just like you have storage acceleration, you also have compute acceleration. So as I mentioned earlier, GPUs are used in these compute nodes. So certain portion of your code or certain portion of the computing can be offloaded to this GPU based node. So when a HPC program is running, it is running on the compute nodes, it is running on the GPU, and the masters are running, master program is running on one of the compute node which distributes the code and data and then gets the job done. So now this is the complete computing environment, but to manage and to run jobs on this compute environment, you need few more things, but what I've shown first is a tape library that is used for backing up the storage. So apart from this, we have what is called as login nodes. So the users, they do not directly jump to the compute nodes, but they will land on the login nodes. And from the login nodes, they will fire the job on the compute nodes. Similarly, for the system administrator, you have the management nodes because these are headless. They don't have keyboard, mouse, anything. They are just stacked together as I shall show you in a picture. And the management nodes will be used by the system administrator to manage all the elements of the supercomputer because the nodes are large in number. And where do the users get onto the login nodes? There will be a gateway, there will be a firewall, and from there the users will log into the login nodes. They will fire the job on the compute nodes. So such a complex supercomputing system needs its appropriate software stack. So the OS is typically Linux, a stripped down version of Linux. Then you have middleware, which includes the monitoring tools that keep track of whether the network, the cluster is in good health. The provisioning tools, like as mentioned, the user fires a job. He tells I want 4 nodes, I want 8 nodes. So that is known to the provisioning tools, which nodes are free, which nodes are occupied, and the free nodes are allotted when the job starts. The file system, it is of two types. One, NFS is the home area, which is our standard serial file system, whereas Lustre is the parallel file system. And when the jobs are run, who runs them? There is a program called as Slurm, which is a job scheduler, which is also works with the provisioning tools to run the job on a particular set of nodes. So that's the middleware, the tools that come with the HPC systems. Then comes what the user uses. It begins with application libraries which are linked to the code. Then there are development tools like either you can use open source GNU tools, or if you have an Intel based cluster, you can use Intel Cluster Studio, which contains linkers, compilers, and other standard development tools, including debuggers. Then while your program is running, you need to see whether it is running optimally. For that, there are performance monitoring tools which help you in finding out how much time a job is taking, how out of that, how much time the CPUs are idle, all that can be seen through the monitoring tools. Now let us see physically what are the things inside it. There are processors. Processors are connected to large amount of memory. A processor plus memory is within a node. Many such nodes are connected using system area networks like InfiniBand and PermNet. There are some specialized nodes that contains coprocessors or accelerator, and the data and code for this comes from storage subsystem, which essentially has an element related to parallel file system. So that's the hardware part of it, which has to be complemented by the system software containing OS and compilers. Then to support parallel processing, either you have libraries or frameworks, which I shall explain later, like MPI, etc. And finally, the application software that runs on this layered architecture of hardware followed by software. So let's now quickly go through how the whole thing looks like. So this is a series of racks that you have, and each rack contains nodes. So this is the rack. So each element here is a rack like this. What will go inside this, what is stacked inside this, is a node like this. Typically this height is 2U. The rack is 42U. So you can have, let's say, some 20 such nodes in this rack. Now what is inside this node? Inside this node is a motherboard like this. So this motherboard has got, these are the slots for memory, and these are the sockets for the CPU, and these are the slots for IO. Like any computing system can be modeled in terms of CPU, memory and IO, and this is a server class machine with dual socket motherboard. So this motherboard, as I mentioned, goes inside in this box. Many such boxes go inside this rack. Many such rack form the complete supercomputer, and they are connected using interconnection networks like InfiniBand. So here each one of these socket will take a CPU like this. Now what is inside the CPU? Inside the CPU there is a multi-core architecture. There was a time when each CPU contained one core, but as per Moore's law you got more and the transistor density increased, and as a result we got more and more transistors. So the designers thought of having multiple cores, which has got its private cache, and there is a linked level 2 cache. So multi-core architecture has got more than one independent processing unit. Each has its own local cache, and then there is a common cache, and then this goes out on the external bus. How does it get? What is the architecture that is followed? So this architecture that you have is typically having multi-core, as I mentioned. So you have this multi-core architecture inside the CPU, and then it gets onto the motherboard, and you have many such motherboards that makes a parallel computer. Now once you have this parallel computer and the tools that I mentioned, how will you write this code? How will you design your algorithm to extract this parallelism? So there are two ways of doing it. Okay, so one is called as implicit parallelism, and the second one is called as explicit parallelism. So what is the difference between the two? The implicit parallelism is one that is exploited by the compiler and the runtime system. So normally what you do is you write a serial code, let's say code in C, to sort 100 numbers. Then the compiler will generate the code, and the compiler will link the external libraries. The linker will link the external libraries. You have the object code out of it. Then it gets converted in an image which the operating system will run on a CPU. Now let's change the scenario from a single CPU system to you go to a system that has got many CPUs or many cores, hundreds of cores. Now the compiler, what it will do is it will generate the code in such a way that it will detect the potential parallelism. Like instead of 100 sorting 100 or processing 100 numbers, suppose you have a task to do which is about let's say adding two matrices. Now you know how the matrices are added. The corresponding elements are added, like A11 is added to B11 to get C11. Or if you have now A11 going up to ANN and BNN, then CNN will be equal to ANN plus BNN. Now each of these additions is independent of each other, and if you have a matrix which is 1 million by 1 million, then you can have parallelism such a way that, let's say, 1000 by, it is divided into multiple 1000 by 1000 matrices, and each of these matrix is allotted to one processor. So who is doing that? The compiler is doing that, and the compiler is assigning the tasks to independent processor. So all that is done by the compiler. The user has to just give a hint. So the programmer just gives the hint. So he's not worried about how the program is getting executed. It is a very general and flexible solution because the compiler is handling the parallelism. However, because the compiler is doing it, it has some limitations, so it cannot be a very efficient solution. That is the disadvantage. Compared to implicit parallelism, you have what is called as explicit. So now, as the name suggests, it is the programmer who has to find out which are the tasks which can be done in parallel. So define those tasks, then assign the task to as many processors as you have. Then also do the execution and synchronization. Remember, in the previous case, all this was done by the compiler. But the good thing about such a explicit one is that the best possible performance can be achieved through explicit parallelism, because it is decided by the programmer what is the parallelism and how to achieve it. But the disadvantage is that the programmers have to be very expert and they need to have a deep knowledge of the computer architecture. Otherwise, to begin with, one can use implicit parallelism and then move over to explicit parallelism and use the appropriate tools, ones that are meant for implicit or one that are meant for explicit. So this is more at the theoretical level. Subsequently, we will see how we can do it in a practical way. Okay. So for that, we have some parallelization paradigms. So the ideal situation is, now what is that? We have a pool of processors and we have divided the work in multiple processes. Each process has to be assigned to a processor. Now while the processor is executing a process or a task, it would be so nice if each processor has a unique work to do. That means it is not getting data from other processor. It is not dependent on other processor finishing its task. You assign a task and the task is independently finished by the processor. As a result, there is no communication or no exchange of data between the processes which are running on different processor. And the work assignment is such that once it is given, all of them finish at the same time. However, this is an ideal situation. What happens in practice is that a processor may not have unique work to do. It may be dependent on other processors' work. As a result, there is going to be communication, and you cannot have ideal division of equal work. In practice, one process is going to finish last and everybody else will wait for it to finish the task. That is what happens in practical situations. But there are some known ways of achieving this. One, and these are the algorithms that are used. I will, instead of reading them out, let me just explain them in detail. So phase parallel model. Why do we call it as phase parallel? Because there are number of phases, number of steps, and each step has got two phases. What are those two phases? The two phases are computation phase and interaction phase. So computation phases are independent. You can see that going from top to bottom is a time scale. So computation is happening. Now we have shown here equal time for all computations, but in practice it may be some computation may be longer, some computation may be shorter. So each of them performs independent computation. It doesn't have to, it has got its own data which it will process. After that, there is a time to do interaction. So that is a synchronization. So let's say some data that C1 has processed has to be used by C2, they will exchange it. And they will come to a step where all of them are now ready with the data that they can individually process. So that's where they are independent. So there is a independent phase, there is a interaction or a dependent phase, and this is a blocking communication, means all the processor, one which finishes first will wait. Then when all of them are ready, they exchange the data, then again the new data is taken and it goes. Like this, these super steps, a series of super steps leads to the final result. Then another way is divide and conquer, wherein you have the master task. It will divide the data it has or a task that it has in two of its children. The two children will spawn grandchildren, and now here they are independently running. The grandchildren finish the task, they give it to the parent, and these two parents then give it to their parent, which is the master task. And this kind of algorithm is well suited if you are doing something like quicksort, and there are many similar algorithms that can benefit from divide and conquer. The third one is like a pipeline model. So this is typically used when you have a streaming data. A set of data is coming like audio, video, and then you divide the work into multiple subworks. The property of these subworks is such that the output of the first stage becomes input to the second stage. Second stage does partial processing. Output of the second stage becomes the input to the second stage. So there are three stages that are operating in parallel, but the work division is such that partial processing is done by P, subsequent processing is done by Q, then finally R finishes the task, and a streaming. So streaming data enters and process streaming data goes out, like cryptographic algorithms, or you have MPEG streams. MPEG streams have to be converted into images. So these kind of applications can use pipeline model. A modification of the divide and conquer is process farm model. So in this case, the master divides the works amongst all the workers that he has. So master divides the work, workers independently do the work, and then they return the work to the master. Master then assigns new work. So like this, the master is the coordinator and master is the one who gets the work done. This is you can say a modification of this, where in this case there are no intermediate division of work. The master will give work to all the workers that are present. Finally, you have domain decomposition. So this is useful for solving boundary value problems. Many of the CFD and other applications, they need to solve a boundary value problem. So you have one domain that is divided into subdomains, and each subdomain is assigned with its program and code to a particular processor. So these are the standard paradigms that we have, and you can have a combination of this in real life situation. So anytime you are designing a parallel algorithm, there are some attributes that you need to see. First is the concurrency. If there is no concurrency, then you better not attempt it on a supercomputer. As much concurrency you have, so many multiple tasks you can do, because you have multiple processors at your disposal. The algorithm should be designed in such a way that today it runs on 4 processors because you have 4 at your disposal. Your data increases, you have access to 16 processor. The scalability should be such that increasing the processor count helps you in using it for solving a bigger problem, or the same problem can be solved more quickly if you have more number of processors. The algorithm should be such that the processor should be working on its local data. I have said that enough number of times that if communication can be avoided, the problem will be solved faster, because accessing memory of another processor has its own time overheads. Finally, modularity. That's the thing that any program should have. so that you can manage the program well. You are able to decompose the big problem into smaller components, then debugging, maintaining becomes easy. So when you write a parallel code, what is that happens at a very broad level? The master process starts and you have multiple processors and their memories at your disposal. So you distribute the data to the memories, put the code in the program memory of the processors. The programs run, they use their local memories which have the data that is assigned to that code. Then use one of the paradigms to organize and synchronize the workflow, and then you if first you get the program running well, get the correct answers, then the next step is to optimize it through computational techniques. Now when you have to do this, what are the frameworks that are available to you? The simplest one is OpenMP, which works for the shared memory computer. Like one node that I described is a shared memory computer. Each processor has got, let's say, 16 cores. So total on the motherboard you have 32 cores. All 32 cores have got access to, let's say, 256 GB of the memory. So you have a compiler that will make the 32 computing elements work on the data that is put in the 256 GB of memory. When you have multiple nodes, OpenMP does not work because it works only on the shared computers. When you have multiple node cluster, how do you connect them? Using InfiniBand or ParamNet. So these are distributed memory computers because each node is complete in itself. So MPI is the way to go. MPI stands for message passing interface, and there are libraries that needs to be linked. There is a runtime of MPI that helps you in running the code. Now, if you don't want to get into these nitty-gritties of using explicitly parallel or implicitly parallelism, then you can use OpenACC, which works with accelerators. So if you have accelerators like Nvidia's CUDA, that is GPUs, or you have from Intel or AMD, then OpenACC is the one that you can use. So it's again compiler directive based, just like OpenMP. So task of the user is easy. Now that you have these frameworks, again, as was told in the beginning, in the opening welcome address, we are going to have this one-day workshop is going to be followed by face-to-face workshop where you will have access to all these kind of frameworks and you will be doing assignments on this. So that's the best way of using these frameworks is to learn these frameworks is to through hands-on sessions. So finally, how does the actual parallel programs are written? As I began in the at the start of the lecture, I mentioned that you have certain domains in which HPC is used, like weather forecasting, computational fluid dynamics. So these are basically mathematics. These are basically algorithms. Like you have physics experts or mechanical engineering experts or chemical engineering experts. These are the domain experts who understand the algorithms. And there are computational experts, computer science students or computer science research scholars who know the architecture. They work as a team. And first they begin with defining the algorithm which is parallel. They find the parallelism in the algorithm. Then the algorithms get converted into the codes. The codes then are ported using OpenACC or MPI or OpenMP or a combination of them. And that's how you get a parallel program. Now, one parallel program may not be enough. There is something called as workflow. That is, the output of one program goes as an input to another program. So these are available as open source. Many such, let's say, programs, open source programs like OpenFOAM is one, or there is one on molecular dynamics, NAMD. Many such programs are available which you can use, or one can. ANSYS is a proprietary. So open source, you will have to get support from the community, but you don't have to pay for it. Proprietary ones could be costly, but then they are support is available for them. So what is the summary? Summary is that HPC is there in our day-to-day life. And many a times, like you see the weather forecast in the news that comes on Doordarshan at 7:30. At 7:45 they tell the next day's weather, but the IMD predicts weather using supercomputers. And the basic principle on which HPC runs is parallel computing, multiple processors, and a supercomputing cluster is one of the most popular architecture today. But apart from the compute elements, we saw that there are many other elements other than the core ones, like login nodes, boot servers, etc. That makes a complete computing supercomputing facility. And to make use of this, you have to design algorithms that are parallel in nature, and we saw some of the paradigms that are commonly used. And finally, to put it to actual practice, you have frameworks like OpenMP, OpenACC, or MPI. That's all I have. Let me see what the time is. Yeah, we have 5 more minutes to take some questions. And I am open to questions now, and you can also mail me if you have any doubts or anything that I covered but you didn't understand. Either you can ask now, or you can call me, you can mail me at this address. So I am open to taking questions now. Are there any questions for me in the chat? Okay.
Yeah, there are a lot of questions in the chat.
Okay.
So,
okay, is there any mechanism to synchronize the computational rate? Okay, so as I mentioned, it has to be a part of your program. Okay, in the sense that you have to explicitly divide your algorithm into a part which is independent computation, and when the results are ready of the individual processing elements, that's the time it will be synchronized. So it's like this, that depending upon what the algorithm is, the time that the program is running, most of the time it will be doing independent computation, and very little time it will take for synchronization. And we'll say that this is a step or a super step, which consists of 2 individual steps of synchronization and computation. And many such one after another super steps will lead to your completion of the program. I think we can even, if the participants are not many, I think we can even allow them to unmute and ask.
yes, they can unmute and ask.
Sir.
Yes, go ahead.
Sir, I am a faculty of NIT Arunachal Pradesh and the co-organizer of this program. Sir, thank you for this nice introduction to HPC. This was very useful, sir. I think I am actually maybe new to this topic. So the one portion which was apart from the hardware, other things was really nice, and I was able to connect it. And probably the hardware also I can go through maybe 1 or 2 times and I can understand. So complete process of HPC. It was really nice presentation, sir. Thank you once again for your presentation, sir.
Yeah, I'm happy that you could connect with it. Thank you very much for your comments.
Yes, sir. Sir, my question is, sir, actually being NIT, there are a lot of topics which you have mentioned. So, and all those topics were interesting. Sir, what I am thinking is, I want to take this to the students so that students can actually start from their UG level itself. So, small, like, sir, weather report, then you told about space, then fluid dynamics, so then bioinformatics. So all this sounds very maybe abstract to BTech students, even for me, but at a smaller level, small models, so which we can learn as a faculty, and which we can pass it on to the students at UG level, so that they get matured by the PG level, and by becoming during the in the course of research scholar, they will get even a much better grasp. So small models, we want some introduction, sir. I want some introduction. So how it actually connects with that parallel programming.
Yeah, so Professor Sinha and I are working on this, and our aim is to train the faculty. We will have a program specially for that, including what you can. I assume that you are autonomous, your institute is autonomous, so you can introduce courses, design courses, and introduce them. So it will be our privilege to help you with this, including we can make the computing systems available to you for your systems to do hands-on session. So the complete cycle, right from designing the course, equipping you with the knowledge, and then giving mechanisms for you to deliver and your students to do hands-on. That is the complete thing that NSM aims at, and I'm so happy that you are willing to take this up. And rest assured, both Professor Sinha and I, our job is to make sure that you are satisfied with taking this to the students in every possible way.
Yes, sir. Sir, I have not yet finished, sir. Sir, actually, I cannot thank Sinha sir enough. That is one thing, sir. So coming to the question, once curious thing, sir, we at Arunachal, we are having 4 kinds of varying seasons, sir. So right now it's again a rainy season, sir. So it's actually we are moving from winter to summer. So in between this spring, there is a rain of say 25 days, heavy rain. And you may be knowing in Northeast, the geography also is different. So I was actually thinking about this weather forecasting, sir. So this weather forecasting, even if we start at a small level, I think this will be very useful. Also considering the biodiversity, considering the geography, considering the variation in weather, it will be very interesting, sir. Sir, one thing in Arunachal, what happens is during this July to September, there is a drastic change in the climate. Suppose there is too hot, maybe for a day, maybe for 6 hours, it's too hot. Then it suddenly changes, and then there is a rain for maybe 45 minutes. Then again, maybe 1 hour. Then the clouds will clear. Then what happens is it will seem that there is no change in the weather. So such things happen, sir. It's a unique geography, and
right. So I think we can. Sorry to interrupt you, but we have a session in the evening for longer discussion. We should not be eating up into the time of the next speaker. As well as if anybody else has any quick questions, I will take them. I didn't mean to be rude to you or interrupt you, but we have a dedicated session for such long discussion at the end. So we will take your question up. If you have any quick question, you can ask it now, or we can allow others.
So I just wanted to make this comment. Okay. So we can have that discussion during the afternoon, sir.
Yeah. Yes. Either 4 o'clock or something, we have it. So we will discuss in detail. And if you are talking about weather forecasting as one of the things, we have a team at CDAC Pune with whom I will connect you. Okay. So they also do localized weather forecasting, so you can benefit from them and you can possibly work on that as well. Okay.
Yes, sir. Yes, sir. Thank you, sir. Thank you, sir.
Okay. Any other quick question from the participants?
Sir, what are the research and development is going on HPC? Because it is presently, what are the actions we are taking on HPC?
So that we will. There is one discussion about NSM's details that during that I will explain, and we have a session by Professor Sinha also, which talks about how to do that research part of it. So I think after that, if you have any questions at that time, I think we will answer them. Right?
Okay, sir. Okay. Also, what are the technology, latest technology we are working? Suppose you are say Yesterday technology and tomorrow and
Right,
day
right.
after daily. So that is also important.
Yeah, so I'll answer that. I will answer that. So what's happening is there are improvements that are being done in the CPU architectures, in the accelerators architectures and networks. So each of these elements that I explained to you. So like if you let's say try and see for example networks. So when CDAC started, we used to have networks that would run at something like 50 or 30 Mbps, 50 Mbps. They eventually became in gigabits. Today we are designing networks that are running at 200 gigabits per second. So what's happening is because of that, the uh, transfer of data between memories of the processors is happening faster. So that in turn helps in running the code faster. Similarly, CPUs that were earlier running at let's say 30 megahertz, 40 megahertz, the earliest ones, now they are running at let's say 2 gigahertz, 4 gigahertz, like that. Similarly, earlier we didn't have multi-core processors. Now you have processors with some of the processors have got 32 cores. So point I'm trying to make is each one of these elements are having its own roadmap, and together they are contributing to the overall speed of the processor. Then of course one more thing which is currently being done is trying to control the electrical power that they consume. So efficiency. So all these things are improving, and some of the things Bharat will tell how many cores, the CUDA cores you get today, how it has changed over a period of time. So to give a quick answer to your question, uh, technology improvements is happening at each of these micro levels, which is resulting in overall improvement in the performance.
Thank you, sir. Last question regarding
Yeah.
cyber security. Whether cyber security plays a vital role in this HPC domain?
So cyber security is one of the problems that can be, some of the problems of cyber security can be solved in using HPC. And if your question was related to security of the HPC system, then there are adequate measures in place to make sure that there are no attacks on it, or only authorized persons get access to it through certain mechanisms. Okay.
Is there any chip level designing stage we can taking care
Of cyber security?
Yes, sir. Yes, sir. Yes, sir.
Okay, so it's like this, that suppose you are saying that if there is an access to these systems which people are not supposed to have, that is illegal access or something, then there are multiple levels of security that are there. Maybe in the evening I will explain that what is that. Okay, so I will answer that question maybe later.
Okay, sir. Thank you for your reports.
Okay. Thank you, Ashish ji, for the talk and for answering the questions. We will move on to the second session. So the second session is a talk on graphics processing units, GPUs, as they are known in short form, and their application in high performance computing. This session will be conducted by Mr. Bharat Kumar Sharma. Bharat is a GPU advocate at Nvidia in India, and he is very active in the HPC community in the country. He has been organizing and has been part of many hackathons and boot camps organized at IITs and other places in the country. So he's one of the most sought after resource persons with respect to GPUs in the country. So I'm happy that he has managed to spare time on Saturday for this talk. So over to you, Bharat, for your session.
Thank you. Thanks a lot, sir, for inviting me again. I think it's always a pleasure to talk to students and the faculty members. I hope the screen is visible and you can hear me clearly.
Yes.
Okay. So welcome every presentation is going to get focused primarily on what is high performance computing and what is Nvidia's view or industrial view from a point of view of the definition of it today. When I talk about high performance computing or supercomputing, we are talking about different sets of application, because supercomputer is not used for one type of application. It's used for different types of application. It may have something related to compute lithography, It may have something related to edge computing. It may have something with respect to creating the next generation of supercomputers. And then you need to simulate it in the current generation supercomputer, which is quantum computing. It may have something related to genomics. It may have something related to computational fluid dynamics, or it may be something where we are trying to create a digital twin of some of the simulations like Earth 2.0, climate, turbine, or so on and so forth. So one thing which is very important to understand is the fact that a computer or a supercomputer is used for different types of applications, and hence it needs to be serving all of those needs or different sets of I would say the users, and that is what drives the industry, I would say, because it is not just about solving one problem and making a chip for that purpose, because the history kind of also shows that if you create a very specialized chip or or something, there's not enough market and it's not sustainable for any of the semiconductor processor or a platform company to survive in a long term, right? So the workloads of modern supercomputers or high performance computing is varied, and they all have been in this form, but there are fundamental changes which are happening that we foresee, we saw some time back, and which is the current reality, and that's why you would see the GPUs are kind of one of the architectures which solve this purpose very efficiently, and it kind of brings in the good aspects of combining all of these workloads together on one processor. Like, one of the most important problem that is being discussed at this point of time is not to create a supercomputer, but to create a supercomputer which is sustainable, which is power efficient, which is green in nature. And I will talk about that in a bit. The second part of it is the generative AI part of it. And all of us at this point of time who are in this industry, whether I know high performance computing or not, many of us are talking about Chat GPT, and why is it different and how is it changing a lot of landscape? Because the way we write softwares have changed. In fact, it has shaken up many industry verticals. It has shaken up many things, and people have started discussing about what is the future of how things are going to be done. So it's an industrial revolution which has come with the advent of AI. Last but not the least is the digitization part of it. No matter how much we say, I think one of the most important thing about it is also to visualize it in a digital form, because and that's where the digital twin part comes in the picture. And if you'll see, when you talk about industry, whether it is Siemens, whether it is BMW, or anything else, or whether we talk about automotive industry, you can't keep on crashing the car for testing all of this. You need to do all of the simulations in a virtual environment, and you can design a building like the Nvidia headquarters was completely designed inside a virtual environment. People were present virtually inside, and then finally it was converted to a physical place where people started actually going there. It does a lot of things, and that's what digitization is all about. So when I'm talking about all of this, one of the things that we need to look at, or the way we are teaching or the way we are actually communicating, is to write softwares in a different way. So we need to build software in a different way. And one of the aspects of it is kind of shown here, where AI comes into the picture. One of the simplest example here is, if you look at this particular image, it shows a human eye will be able to very clearly see that there is an atmospheric river on this particular image. But for a computer or for anybody to write an algorithm, it's very difficult. And AI is very good at solving some of these complex problems, which may in certain cases where we don't even have an expertise, or we cannot explain our expertise. Like, it's very easy for us to speak or understand each other's dialects, but it's very difficult to write an algorithm which can do this. But AI can do it really, really well. If the solutions keep on changing very fast, or if the problem size is too vast to be calculated, AI has proven a new way of doing this. Or what everybody is talking about, and ChatGPT has kind of also showed the impact of it, at least in the textual form. There are different versions of it, but since everybody knows it, I'm just using the word ChatGPT here. So we were teaching everyone, like there is a programmer, we used to teach them how to write C program, Python code, this, that. There was some knowledge expert who wrote some algorithms, and that knowledge expert gave the mathematical equations, and then the task for the programmer was to convert that into a human readable function. And the cycle was you give it the input data, and the programmer has written the logic and used to always get the output data. But with software 2.0, as we call it, as where the software itself writes software, it works in terms of examples where there is a node which is called as an optimizer, which takes or learns based on the experience, and basically it spits out a machine learned function. And if you see your overall scenario has kind of changed, where you have input data and you have output data, and the output is actually the logic itself. So the computer is actually generating new generation of codes. Today, AI can write not just simple codes. If you tell AI to actually write a fast Fourier transform, it should be able to write a fast Fourier transform for you, write sorting algorithm for you. So how do we change our approach towards even teaching on how things are going to be forward is very, very important. Let me give an example. There was a question about climate, and let me give you an example of on how this is working around the world, at least at this point of time, apart from the traditional approach. So in the traditional approach, you will get certain input parameters like temperature, pressure, moisture. The output of that is the probability of rain. And then a software engineer comes and basically takes all of those mathematically provable functions and converts them into handwritten functions. Like updating the mass, momentum, energy, basically writing all the partial differential equations. While the reverse engineer approach, which is from the AI world, is instead of having those traditional functions, you basically have other kinds of mathematical equations like ReLU, sigmoid, so on and so forth, and it has some uninitialized weights. And then you basically train the network iteratively via this optimizer in a way that these functions start behaving the way actually somebody would have actually written that code, handwritten that code. And that's the learned function approach rather than writing the traditional simulations. And both of this exist on your supercomputers at this point of time. We were talking about the definition of how it has changed. Let me give you a definition of it from a perspective of how things happened. In 2012, the deep learning framework, AlexNet, won the competition, and it basically used a neural network which had 61 million parameters. In order to train this network on a single GPU, took them a long time. But if I convert that into petaflops, or in terms of flops, it took almost 262 petaflops to train this network, and in the end, it won the competition by a large margin. Now, this was in 2012, right? And this was the necessity of the hour, where without GPUs today, you can't even do this, because if you do it, you are practically making yourself sequential in nature. And I think even if you want to do any research, I think you would be always slower, because it just takes too much of time to do anything. Today, when we are talking about the newer networks, the GPT-3 model, basically, if you see the previous model has 61 million parameters, today the GPT-3 is 175 billion parameters, and it takes not one GPU, but the new definition of a supercomputer is basically, even to train a network, is one whole big supercomputer, here in this case a DGX pod, which has so many machines, and you need to have a whole cluster to even train a network and make it reach a state where you can use it. And the amount of time or the calculation it takes is 323 zettaflops to train 175 billion parameters. So when we are talking about supercomputing from 2012 for now, there has been a growth which has been so tremendous that it cannot be possible without using high performance computing or parallel computing architectures like GPUs. And that's the growth we are talking about at this point of time. If I talk about a cycle from Nvidia's perspective, what Nvidia believes in, and Nvidia being a developer-centric community, we enable all of the developers via our framework, which is CUDA, Compute Unified Device Architecture, which helps the developer to run these codes on, say, embedded device like Jetson, which goes inside autonomous driving cars. The same code will work on your workstation. The same code will work on a supercomputer, or the same code will also work in a cloud. And that's what one of the things which made CUDA or NVIDIA platform as one of the most sought after parallel programming computing platform out there. And because the developers have access to it, they can practically go like the LXNet. Basically, no NVIDIA engineer went and parallelized it. We just taught them how to write parallel code. They went and applied it to a new domain, which was deep learning. It was invented by the researchers, and that's why a new thing was born there. And that's the ecosystem that NVIDIA has developed. Let me give you a vision for HPC, the true vision of HPC, which is the necessity of the hour. Suppose if you are trying to do direct numerical simulation for 3D combustion, so you would basically use some of the modules, say in Fortran or something like this. Or if you want, you can use Python and use NumPy for creating 4D arrays, 5D arrays, and help to solve some of these differential equations, right? Once you are done with it, you might also give it to some other entities, like you might give it to pandas for doing some statistical analysis, like you may group some of the chemical species together, right? And the output of that is given back to your simulation in the real time for doing uncertainty quantification. And you might also want to visualize this grouping, say in another tool, which is Matplotlib, right? Or you may also approach to reduce the simulation time by applying some of the machine learning techniques along coupled with your simulation, and you might end up using another entity like scikit-learn, which may do some part of your job, like recognizing the flame wavefronts, or it's creating basically a cluster to help you fasten your simulation. And in the end, yes, you would again like to visualize it, and you might use an entity called as VTK. And if you see, what I'm trying to tell here is your HPC simulation end to end doesn't require just one type of software. It requires a collection of softwares, and it's a pipeline. And in what happens in the real world is that you will basically use, say, an MPI based application for doing the first part of it. You will run it on, say, n number of nodes across the whole supercomputer. Then when you move from this stage to the other, you cannot do it real time. You will write all of this output of simulation, and you will do file IO, which is completely IO bound, resulting into a lot of overheads in terms of writing. Then you will again run your analysis of machine learning pipeline on certain number of nodes. Again, you will write it to the disk and then move on to the next one, which is visualization of it. First of all, the visualization cannot be even done on a traditional machine in case it doesn't have capability of graphics, because you're trying to do large simulation graphics and not just a simple one, right? And this is what happens today, and this is what has been happening. So you can see the problems with all of these pipelines, right? So there was a question on what's happening towards the research, right? And that's what I'll try to say. Like, The user expects if I talk about any user would like to write a sequential program. Nobody would write to learn parallel programming. They would like different set of softwares to talk to each other, and it should be running across different hardwares. And what is required for that is to have implicit parallelism, not explicit parallelism, but implicit parallelism. Implicit parallelism means that the framework behind the scene takes care of parallelizing your code or distributing the data and communication, and all of those is taken care by the framework, and you don't have to do it. And for that to happen, you need to have composability, which means different components should be able to talk to each other. They should be self-sufficient. And if I have 1 node versus 10 node, it should be able to scale automatically rather than me having to tune all of those things. So this is the expectation, and this is what the community or the research community needs to deliver. And one example of that is the new active research, which is going from hardware out of order processor execution to a software out of order execution. What it means is that you write your software at a very high level, like what is the task I want to do? What is the data I'm going to use? Which task talks to which data? And let the framework divide the task and data across your cluster in a way that you don't have to manage it. It will take care of things like overlapping the computation with the communication and so on and so forth. And the new way of writing this code is what should be ideally taught to the new generations, because there are already frameworks who do this. So if anybody is going to write new piece of softwares, they should be using this model rather than the traditional models which existed. The legacy codes will continue. There's nothing that we can do about the legacy codes. They cannot use this new model, but it is the responsibility of having all of this incorporated into the new generation of curriculums, because without this, again, we'll be teaching them the old way. And when they go and write their own code, they will again start writing in the old way and not take benefit of all of this newness which have come out of all of this research which is there. And once you do that, there are different things which can happen. Like one example of it, which I was also talking about, that Nvidia, if you look at we talked about the top 500 supercomputers, but there is another list which gets published, which is called as Green 500 supercomputers. Green 500 supercomputers are the list of supercomputers which gives you the best performance per watt of energy that they use, per amount of energy that they use. And if you look at that list, they are primarily dominated by accelerators like GPUs, and most of them are Nvidia GPU based, because they were purpose built for being energy efficient. They were always green in nature. You can see in this particular example that in this particular case, we are talking about a CFD. So if you convert your code to a traditional architecture to say a CUDA based GPU, you can see here at the same cost, you have a choice of getting more amount of performance, or you can save 9 times the cost because it saves you energy. Please mind that buying a supercomputer sometimes may be easy, or it's not that costly, but maintaining that supercomputer is very, because it needs to run 24/7 and it consumes a very large amount of energy. If you look at the energy consumptions which are coming from the data centers and supercomputers, is almost reaching 10% of the global energy consumptions. So this is a big problem, and everybody needs to solve this problem together. And that's the research which is happening, or that's where Nvidia has been committed from the top, and that's why it is on the top list from a point of view of being green, not just being fast, but also being green in nature. Now, there was another challenge which is very important for not just for the industry, but also for the academics to understand, because finally the same students will join the industry. And the reason behind that is to understand is the fact that almost all of the industry understands the fact that they need to use AI. But almost many of them also understand the fact that there are challenges in adopting AI. And that's the gap which academia is solving today at this point of time, with help of training the students and doing research in this particular direction. From Nvidia side, how do we do that? one of the most important thing which I brought out previously also is that we don't expect everyone to know parallel programming, or we don't expect everyone to write parallel programs. We expect them to use libraries, frameworks, the work which has been done over years of past decade to make sure that you don't end up reinventing the wheel. And if there is already a library out there, you don't need to do it. And one of the reasons why AI is successful is because nobody writes, say, a backpropagation algorithm, or nobody writes a convolution algorithm. They just use libraries like TensorFlow, PyTorch, and just write their domain or create neural networks. If you would have told everyone to write their own convolution neural network, you would have seen the pace at which this space is moving would not have worked. And this is one of the most critical things that everybody should understand, is the availability of different sets or generations of frameworks out there. To give you an example, Nvidia has a library called as Quantum, which we have recently made also open source, which is CUDA Quantum. You can go to GitHub and download it, contribute to it if you want, because it's under BSD license, where you can basically go and do simulations of quantum. You can do quantum simulations on today generations of GPUs. So you are creating a new supercomputer. You're trying to create new algorithms like quantum machine learning and all, which will work on next generation supercomputers, but you need to simulate them today. And you don't need to write from scratch because there is already a framework out there for you to do this. We are also talking about power efficient computing. Let me just bring to you one of the aspects of it. ARM has been one of the most popular architectures out there in the mobile industry. The reason why it has been really popular is because it is also very power efficient. Because one of the main things about power efficiency about mobile industry is that no matter how fast the processor is, if it is not power efficient, it will consume a lot of battery. Nvidia has created a chip based on ARM architecture, which is called as Grace. And if you see, there is a chip which we announced this week. In fact, GTC is ongoing, which is Grace Super Chip, which has 144 cores of the ARM cores. And the reason for this is quite obvious. As I said, ARM is one of the architectures which has proven itself to be really power efficient. So you will see newer generation of architectures coming out where it's basically concentrating on the power efficiency part of it. To just show you an example on what do I mean by that, when we run the simulations on the Nvidia Grace versus one of the next gen traditional architectures, you would see for different sets of services like Google microservices or big data, either you can get more performance or you can get up to 70% power efficiency. What does it mean? Actually, if you see for cloud vendors, it is very important because most of their money or the amount of expenditure goes in cooling or making sure that the overall thing is running by the power. 70% efficiency is a very large number for any of the cloud vendors out there. So if I talk about the new generation data center, this is how it will look like, which Nvidia calls as a modern AI factory. But it starts with one GPU, where we have a GPU, like in this particular case, I'm showing you a Hopper GPU, which has few thousand GPU cores. And that's what is the fundamental difference, which was brought out by Professor Sharad, which is like GPUs as an architecture are built where you have thousands and thousands of cores. So you can launch 10,000s of threads in parallel on the GPU. And it has its own advantage when it comes to running it on a GPU architecture, because it can handle so many parallel operations in together. And that's one of the most key fundamental thing about the GPU part of it. Now you can combine all of these GPUs together and have a particular high-speed interconnect. There was a talk about the interconnect. We have high-speed interconnects within the system, which is called as NVLink, which can give you few terabytes per second interconnect, because no HPC currently runs on one architecture or one processor. They need to talk to the other processors. And when they talk to other processors, no matter how much fast one processor is, they need to talk to the other processor. Otherwise, you will be communication bound and not computation bound. So hence, you need very fast interconnect within the system and across the system. Like NVLink provides you a few terabytes per second. And you can have one big GPU like this. This is an example of a DGX system, how it looks like. And IIT Goa has one of them at this point of time. You put this DGX system into one in this rack, and then you connect all of this DGXs together via this high-speed interconnect like InfiniBand. As sir gave an example, today you have InfiniBand going up to 400 gigabytes per second. We are not talking about 10 GB per second or so. We are talking about interconnects where they give you a bandwidth of 400 gigabytes, 800 gigabytes per second, so on and so forth. So it requires a supercomputer requires one node which has multiple processors, and they are connected to each other via this very nice topology of interconnects, which can provide transfer speeds which can match the computing power which is provided in one box. If it cannot do that, then your application will be slowed down because of communication and not because of computation. And this is how a DGX supercomputer kind of looks like. And this is what we call today as the minimal unit of an execution, because as I already told you, the calculations that we require for proceeding the research is in zettaflops, not just petaflops, but already it has surpassed zettaflops. So, and this is how the modern supercomputer kind of looks like. This is a snapshot of how it will look like in the real world. Just an example, like you have all of these big power cables coming out, all of these wires going out are basically your InfiniBand connections. You will have Ethernet connections as well moving around. So I know I would not have a lot of time, but I would like to tell you how things are changing. What you're seeing here is a snapshot of how much time it took to reach 100 million users in months, right? So you're talking about how can you reach 100 million users in months? Like for WhatsApp, it took 49 months, so on and so forth. TikTok, it took 13 months. And the new big bang, which is the chat GPT, it just took 2 months to reach 100 million users. And this is one of the biggest success stories that you see today. And it can do a lot of funny stuff. It can do a lot of powerful stuff as well. And as I said, it has billions of parameters which needs to be trained at this time. So what I'm trying to show you is how things are changing so fast. So the industry and the academia needs to come together to make sure we are able to innovate at the same speed here. To give you an example, also, in order to make sure that it is accessible to the whole world, and what Nvidia did was Nvidia created something called as AI Foundations. And if I give an example of an AI Foundations, what it means is most of the stuff in the future will basically be looking like an API service, which means you will have a factory or you will have a particular, how should I say, a store where you will develop your models and you will deploy them and expose them as API. Like the way ChatGPT works, ChatGPT is an API-based framework where you go register, you can use the API to ask it any questions, it gives back the result to you. And it will change. It has already changed the industry from a natural language processing side, computer vision side, or say from a bioinformatics or genomic side as well. Another aspect, which is one of the most important one, I'm not sure, Professor Sharad, if you can confirm, if you can hear the audio as well, would you be able to confirm to me? Can you hear the audio?
No, I can't hear the audio. I think when you share, Bharat, there is also a separate button to share the system audio.
Okay, so let it be. I think I don't need to get into that particular part here. But the next part or the last part which I wanted to also harp on the part was the digital aspects of it. We are trying to digitize or create, say, Earth 2.0. We are trying to digitize the whole turbine. We are trying to digitize a lot of things out there. We are talking about creating a whole digital space for autonomous driving, for software and electronics, design and engineering, concept and styling, or the whole factory itself. And all of this requires not just your traditional computation, but it requires features like real-time ray tracing. Because the new generation, if you look at, I know that one of the industry that you talk about is movies and games, but you won't believe all of them have physics equation written behind the scene, and it requires physics-based equation for doing the ray tracing. And all of this requires a specialized engine, like Nvidia has a special engine or a core which is meant for doing ray tracing, so that you can actually visualize all of those things as if it's realistic and in real time. The same thing cannot be done with your traditional cores. While the traditional cores can do it, but they are not meant for doing it. So, and that's why a coupling of your cores, which is your compute cores, along with the core which can do ray tracing, is one of the aspects which makes GPU also very, very good for running compute, AI, and also say the part which we call as Omniverse. So I know I have exceeded the time, and I know that the audio is not working really well at this point of time. But I will open it for questions. The video will keep on playing, but thank you again, everyone. But if there are any questions, I am happy to take them.
So questions from the audience, you can unmute yourself and ask the question.
Sir.
Yep.
So mine is, I think, a simple question. Sir, can this parallel computing be carried over the cloud?
It's already in the cloud. The good thing about all of this is that today, when we talk about computation, it can be, say, composed into an entity called as containers. And those containers can run anywhere. Like you have GPUs present in Google Cloud, you have it on Amazon Cloud, you have it in Oracle Cloud. So you can develop something, say, on your laptop as a container and deploy it on the cloud, or say on your supercomputer, which is at your desk. Also, like the DGX station, which IIT Goa has. So you can develop it on your laptop to get more performance. You can run it on there, or you can deploy the same container even on the cloud, and it already exists.
Okay, sir. Sir, how do you think we as an institute can contribute to this, or we can get involved in this in research aspects?
So
you actually referred that we need to update the syllabus like that. So what would be the small steps which we need to take?
So we are already doing that. Like from Nvidia perspective, I can give certain examples. Nvidia has a group of, we call them at teaching kits. If you just search for Nvidia teaching kits, you would see that you can go to the Nvidia site. It is particularly for professors. The professors can actually go download those teaching kits. It has pre-bundled presentations, curriculums, how to do evaluations, so on and so forth. So it's like a sample place which is being developed in collaboration with the leaders from the academia. Like Jeffrey Hinton, we made the deep learning course along with Jeff Hinton himself, right? And we have made it as open source. So you have courses on robotics, you have courses on deep learning, you have courses on parallel computing, you have courses on Omniverse, which is the parallelization part of it. The visualization part of it. Also, along with CDAC and all, we work like we keep on doing these boot camps and hackathons together in collaboration. We worked on a particular, I will give an example with IIT Delhi. We worked on a new curriculum which we made open source, which was meant to focus just on if you have a proposition, obviously, to work on physics informed neural network. So there's a new beast which is called as physics informed neural network, which is meant for solving partial differential equations in a different way, which normal neural networks cannot solve. Like it has a component of Fourier, it has a component of other aspects as well. So if there is a necessity, Nvidia also works with them in terms of creating these new curriculums together.
Sir, I don't, if somebody else is having any question, then I will ask next. If not, I have one more question, sir. Yeah, sir, actually, I'm taking, say, numerical methods. Now, I just want to involve this GPU. So what we do is we normally write the codes in Fortran or C++ or even Python. Now, as a first step, I want to involve this parallel processing and Nvidia, whatever, so that I can merge the students and it actually keeps them moving. So I don't want a higher level like robotics, because even I need to study all those, but this I can really connect. So I just want a small advancement in that. Is that possible, sir? So suppose
it is quite possible. The way you would see the new courses are designed. So I work with professors from mechanical department. I work with professors from chemistry department and all. When they're floating a course, they have a component of few weeks dedicated towards writing parallel codes, which is integrated as part of the fundamental course itself. And when they're given an assignment, they're told to write something in parallel and not just write something which is sequential in nature. And it's very easy to do that, like the teaching kit which I just mentioned to you. You can take it, you can customize it for your need and integrate it inside your coursework.
Okay, sir. And do we need if this is cloud based? If this is cloud based, can we do it anytime?
See, when I say cloud based, there are obviously some free instances given in the cloud, but that doesn't mean that everything can be done in the cloud like that, right? So while you'll get all of the course material, you'll get everything, you will also get instances there, but it is limited in nature.
Okay.
Like the compute resources are limited, right? You cannot get the highest resources, but the good thing that NSM has done is they've provided this access to almost all of the users across the country. So you should try to get accesses to these machines as well and not just in cloud.
Okay, sir. Sir, we'd be happy to get your email ID, sir. Yeah, if possible.
Yeah. So I'll provide it in the chat window.
Yes. So thank you, sir.
Yeah.
So Bharat, the free resources that are given in the cloud by Nvidia, that I think would be sufficient for teaching purposes. May not be sufficient for research purposes, but
no. So the cloud that I talked about, Nvidia doesn't have a cloud, right? As in, it's like if you go to Google Colab, it's a cloud. You have T4 instances which are free. What Nvidia gives is the other material that you can go and run there.
Okay. Any other question from the participants? So we will come back to some of this later in my session when I talk about resources, where I will show these resources and how to access them to some extent, so that it helps you in your learning. Okay, so thank you, Bharat.
Thanks a lot.
Thanks, Bharat, for the session, and I hope the participants have found it useful. If there are no further questions, then we will break here for an hour. I think 2 hours. Okay, so welcome everyone to the second half of today's virtual workshop. I hope I am audible.
Yes, Sharad, you're audible.
Okay, great.
Yes, sir. Yes, sir.
Okay, good. So,
Yes, sir.
in this second half, we will have the first talk by Dr. Sudhakar Yogaraj. His talk is titled "A Parallel Unsteady CFD Solver Based on the Artificial Compressibility Method." So Dr. Sudhakar is an assistant professor in mechanical engineering at IIT Goa, and he obtained his PhD from Technical University of Munich in Germany. He spent a couple of years at KTH in Sweden as a postdoctoral fellow, and even before starting his PhD, he spent some time at the Indian Space Research Organization as a scientist. So I welcome Sudhakar, and over to you, Sudhakar, for your session.
Thank you very much, Sharad, for the introduction. Let me share my screen. There is an issue in sharing my screen. Is there any permission needed? No, it's coming. Okay, all right. I hope everybody is able to see the screen and my voice is audible.
Yes, yes.
Okay, all right. Okay. Okay. So very good afternoon, everyone. Thank you, Sharad, for inviting me to deliver a talk in this workshop. So in this presentation, I'm going to be talking about a solver that we have developed in IIT Goa based on the artificial compressibility method. Okay, so the talk will be a mix of some computational fluid dynamics concepts, and I will explain briefly how did we parallelize our code. Okay, so let us start with the objective. So there are many practical applications around us and also in nature that the associated fluid flow can be assumed to be incompressible. Okay, you can see some of the examples here. The first one is flow through our organs. Second one is an urban flow, which is important to model pollution dispersion. Then computation of resistance on the ship, and importantly, in recent times, the electronic chip cooling. In all these applications, we can neglect the variation of density with pressure, and we can assume the flow is incompressible. Okay, and I think in majority of the industries, including automobile and aerospace and so on, the computational fluid dynamics is becoming inevitable part of the design and development cycle. It is slowly replacing the expensive experimental testing. Okay, and Mr. Kuvelkar talked about the rapid growth in computing power in the recent decades. But to make best use of the available computing power, we need efficient algorithm. This is a prerequisite to make best use of all the hardware advancement that we are seeing. Okay, and our focus is to develop a fast, highly parallel, and incompressible computational fluid dynamics solver. Okay. And one possibility is to solve the compressible Navier-Stokes equation directly, the governing equation in compressible, the governing equations of compressible flow, but use them in the incompressible limit. Okay, this is how briefly the equations look like. But the problem is when we are doing that, we are actually tracking a wave that is traveling at infinite speed. So the computational time step should be as small as 0. It will be very close to 0, which is not practically possible. Then the solver becomes very, very expensive. And we have a set of equations available that talk about the fluid flow, that governs the fluid flow in the incompressible limit itself. Okay, where U here is the velocity and P is the fluid pressure. Okay, the challenge here is that there is pressure appearing here in the momentum equation, but there is no separate transport equation for pressure itself. Okay, so mathematically, pressure acts as a Lagrange multiplier to enforce this continuity constraint or the mass conservation. Okay, and of course, the CFD solution of incompressible Navier-Stokes equation is not completely new. There are a variety of methods, including projection methods, simple family of methods, or fraction step methods are available. What they do is they obtain an equation for pressure by taking divergence of the momentum equation. So you will get a Laplace or a Poisson equation for pressure, which is function of the error in the mass conservation. Okay, it works perfectly fine for simulations. I mean, it works perfectly fine from the numerical methods point of view, but this is problematic from high performance computing implementation point of view. Okay, that is because this solution of this Poisson equation occupies over 90% of the total simulation time. So this is the most expensive process of solving the incompressible Navier-Stokes equation. And you can see that there is no time derivative appearing here, so we cannot use explicit time integration, which is very, very good for parallel processing. So the appearance of this Poisson equation for the computation of pressure is a huge roadblock for efficient parallelization of incompressible Navier-Stokes solvers. Okay, and there is a need to circumvent the use of this pressure Poisson equation. Okay, such a method is already proposed long ago. The method is called artificial compressibility method. This is the classical one proposed by Corin before several decades. You can see that what happens is that instead of the mass conservation equation, we solve an evolution equation for pressure. Okay, this is not derived from fundamental principles, but rather what Corin does is he has introduced slight compressibility into the governing equation, and he is able to obtain an transport equation for pressure. Okay, so this solves, this overcomes the problem of solving, because there is no Poisson equation here. So this is very fast, but the problem is it is applicable only for steady state flows which do not change with respect to time. Okay, and that is a big limitation, because in most of the applications that I had shown earlier, the flow is actually highly unsteady. Okay, and this limitation is solved by using what we call as a dual time stepping process, where we introduce artificially a pseudo time derivative of velocity in the momentum equation and pseudo pressure derivative of pressure in the continuity equation. So we can see that the physical time is given as t here, and the pseudo time is given as tau. Okay, so what we need to do is at each time step, we need to run several hundreds of or even thousands of iteration on this pseudo time loop until we get the velocity divergence to be 0. Okay, and this is a very expensive process. Although it is applicable for unsteady flows, this is an expensive process. So we have eliminated the problem of solving a Poisson equation, but we ended up with another problem which is equally computationally expensive. Okay, so in the recent years, there has been a number of methods proposed that avoids the dual time stepping process, and that can solve the unsteady fluid flow. Okay, so this is the classical momentum equation. You can see this equation is called a general pressure equation, which is proposed by Tautent just before 5 years. And so this is basically derived based on asymptotic analysis of compressible flow equations, and it unifies highly compressible flows, low Mach number flows, and the incompressible flow approaches. Okay, so we are going to be so what we have done is we have developed a solver based on this general pressure equation, which has a lot of advantages. As you can see, there is no elliptic pressure equation here. This is a parabolic one. So neither time-consuming elliptic Poisson equation nor dual time stepping is actually needed to resolve unsteady incompressible flows. Okay, and it is applicable for steady as well as unsteady flows. And what you can see that there is a time derivative of velocity as well as pressure in the governing equations. So we can use explicit time integration for the solution process, meaning that the solver that we develop based on GP is highly portable for parallel computing. There is no need to assemble a matrix or do any matrix vector product. Okay, so we have developed a solver based on this. The next slide briefly shows the discretization details. Okay, for the time integration, we have used a third order, the strongly stability preserving Runge-Kutta scheme. Okay, which is which is available in many textbooks. And we use a staggered grid for the discretization of spatial operators. And those who have attended a CFD course or a numerical methods course know that in order to avoid checkerboard pressure oscillations, which will make the simulations unstable and give unphysical results, we need the staggered grid. By staggered grid, we mean the pressure and the velocity components are stored at different locations in the given grid. Okay, and all the spatial derivatives are discretized using second order central difference scheme. Okay, so this is this is briefly the details of the governing equations and the discretization. Next, we will very quickly go through the parallelization aspect of it. Okay, so we have developed a parallel solver using message passing interface libraries. Okay, and we used MPI because it works both with shared as well as distributed memory architecture. So we can use OpenMP for parallelization, which is very easy to implement. But then it is limited only to shared memory architecture, meaning that you can use only one node in your cluster to run the simulation. Okay, but with MPI, we can run the simulation using several number of nodes. Okay, and our code uses a Cartesian grid that you can see here. This is an example of a grid, and we use in MPI libraries there is something called MPI cart. Cart implies Cartesian. We have used this feature for the parallelization. Okay, there are I think 5 to 6 steps involved in the parallelization. Step 1 is the domain decomposition. Okay, by domain decomposition, what we mean is that, let's say this is the mesh on which we want to solve the governing equation. Okay, and we are going to use parallel processing. So what we do is we divide the mesh into different parts. Okay, let's say we are going to use 4 processors for parallelization. Okay, so we divide the mesh into 4 parts and we send them to 4 processors in our machine. Okay, so each processor will know only its corresponding machine. Okay, so the entire mesh is not stored in all the processors, because that will be very memory expensive. So to reduce the memory problem, we divide the mesh into different portions, and each processor will store only its portion of the mesh. Okay, and these 4 implies the number of processor we are using, and rank is their ID. Okay, so that is step 1. You divide the mesh and distribute across processors. The second step is to obtain the neighbors of each processor. Okay, let us say rank 0. It has at the top neighbor 2, and the right it has a processor with rank 1 as the neighbor. Okay, so we have to obtain the information about neighbors of all the processors participating in the parallel computing. Okay, so this can be easily done using this feature called MPI Cartesian shift. Okay, this is a very easy step. Okay, so we need this neighbor information because across this boundary between 2 processors, we will share the information of about the solution update from one process to another. Okay, so this is why we need the neighboring information. So the third step is to solve your discretized equation on the interior nodes. Okay, so here I'm considering only one processor here. The blue dots represent interior nodes, and the orange, or what is this called? The pink one is they are called ghost nodes. Okay, so ghost nodes are essential to transfer updated values from other processors into these nodes so that we can solve the discretized equation at the interior nodes. Okay, so on each processor we update the solution on the interior nodes. Okay, and in order for the computation to go further, the ghost nodes of each processor should have the updated information about the solution. Okay, so let's say we are transferring the data from here to here. So the value from the interior node here will be the value from the interior node here will be copied to this ghost node, and the value from the adjacent interior node from this processor will be copied to the ghost nodes here. Okay, so these are all standard operations that we always use when we use MPI library, because this data transfer is the one that consumes majority of the time as far as the parallel computing is concerned. Okay, this is the challenging one to make it efficient. Okay, so after the data transfer, we compute the error in each processor. So the solution we compute will always have some error. Okay, we compute the local error independently on each processor, and we need to perform some communication across the processor to get the global error. Let's say we are interested in computing L infinity norm, which is the maximum error across the processor. So we compute the error on each processor separately, and all processors will communicate with each other the maximum value, that the maximum error that they have, and out of these values we compute the maximum among them. Okay, this also involves a lot of communication, and then we see if the error is below the convergence criteria we have specified. Okay, so these are the 6 steps involved in parallelizing our code using MPI. In fact, these are the general steps that you need to use irrespective of any solver that you parallelize using message passing interface. Okay, so those are the brief details about the parallelization. Let's move on to see some results. Okay, and the classical test case is a Taylor-Green vortex problem. Okay, we are going to solve this 2-dimensional square domain. The analytical solution for this particular problem is known, and this is a widely used test case to study the convergence rate of the solver, which is a very important a measure of how fast your error reduce if you refine your mesh. Okay, and these are the this is how the initial conditions look like. If I plot these exact solution at time 0, this is how the velocity in x direction, y direction, and pressure will look like. Okay, and we have a number of parameters in the general pressure equation. So we use the Prandtl number to be 1, and also gamma to be 1, and the artificial Mach number we want to keep it as small as possible so that we actually solve for incompressible equations, but it should be slightly large enough so that the time step that we can use is manageable. Okay, so 0.02, the Mach number of 0.02 provides a balance between accuracy and computational efficiency. Okay, so in all our simulations we use Mach number to be this artificial Mach number to be 0.02, and we perform the simulation at a Reynolds number 100 with periodic boundary condition, and I'm going to show the results for a mesh of 64 times 64. Okay, this is the results with mesh size 64 square. Okay, our interest in simulating this problem is to study the convergence rate. We have used second order central difference scheme to discretize a convective, diffusive, as well as the pressure gradient term. So as expected, we get a second order convergence for pressure, for velocity, as well as for pressure when we use GP. That you can see the green line here, it's slightly more than second order actually, and for velocity it is second order. The green one is actually hiding behind the blue one. Okay, so we are getting a correct order of convergence with our code. Okay, that in a way tests our implementation of the discretization process. Okay, the next test case we want to simulate is to test the accuracy in a rigorous manner, and a well-known test case is what we call as doubly periodic shear layer. Again, the simulations are performed on a 2D square domain. Okay, we use these initial conditions. These are the details from standard test case. Okay, so the nature of the initial condition is that there are two regions in the flow field which involves huge gradient across a small layer. You can see these blue and the red line here. They imply a large gradient of vorticity across this layer. Okay, and we perform the simulation at 10 to the power 4, the 10,000 Reynolds number. And this is a challenging problem, so we use a mesh size of 256 square. Okay, and when we do the simulation, what happens is that these regions of very high vorticity will roll up into two discrete vortices, as you can see from this animation. Okay, so they become unstable and they roll up into two distinct vortices. Okay, so this is a challenging problem because to get accurate results, your code should be stable, even with such large gradient. Okay, so actually we are using artificial compressibility methods for the solution process, meaning that we will not satisfy the incompressibility constraint accurately. As you can see that the velocity divergence, instead of 0, we are getting a value as large as 0.01. Okay, so this raises a question about accuracy of the method. But if we plot the total energy content of the problem with respect to time, you see that the simulation from the present method very accurately matches with the other reference data. Okay, so what we see is, despite a large error in velocity divergence, which we intentionally introduced because by doing so we are actually increasing the flexibility to write parallel programming, and despite this problem, the accuracy is very good, as you can see from this picture. Okay, next I'll show a problem which is a very large one. This is called a turbulent Taylor green vortex. Okay, the problem is solved on this is a 3D problem. It's solved on a 2 pi square domain, and these are the initial conditions. We don't have an exact solution for this problem, and Reynolds number of 1600 is a standard test for which the results from other simulations are available. Okay, for using which we can compare the accuracy of our code. Okay, this is a very special test case for us because this is the largest problem that we ran on, to my knowledge, on the HPC cluster at IIT Goa. The simulation uses approximately 135 million nodes, and we have used 256 compute cores to complete this simulation. Okay, so what happens is that the flow starts smoothly from the laminar region. Because the Reynolds number is large, it is subjected to instability, and turbulence will set in, and the turbulence itself will decay because there is no solid wall. This is what we are going to see in this animation. Okay, the flow is laminar now. It is subjected to instability, and you can see small scale vortices will start forming, and the turbulence will essentially decay. The decaying can be understood by observing this maximum, the magnitude of the vorticity. It went up to 43, and you can see that it will reach a very small value. Okay, so this simulation shows that our code can actually run on a very large number of processors. Okay, all right. So whatever the results I have presented are for a single phase. Okay, additionally, we can see that this plot shows the accuracy of our method. Okay, the green one is our simulation, and the red one is the reference data. You can see that there is almost 1-to-1 match between the current data and the reference value for the decay of kinetic energy of the fluid within this domain. Okay, all right. So until now, whatever I have presented are for accuracy. From a computational point of view, what is important is what we call as scalability. So scalability is a measure of how efficient your parallelization process is. Okay, so it is actually the ratio between actual speedup and the ideal speedup. Okay, by ideal speedup we mean if you increase the number of processor by twice, then we expect that the speed of the simulation will also increase by twice. So such a linear speed up is very ideal. We will not be, in general, we will not be able to get it. Okay, there are two ways to check the scalability. One is a strong scaling. Okay, even in strong scaling, we fix the problem size. In our case, we fix the number of nodes and we increase the number of processors and see how fast the simulation is becoming. Okay, and this is the Ahmed law is very important for this, where which is given here, where SP is the speed up with P number of processors and F is a serial fraction of the code. Okay, so no code can be 100% parallelized. There are some parts of the code that we cannot parallelize. We have to run it in serial mode. So how much of that serial mode we have in our code is what is given by F here. Okay, so we studied this for the turbulent Taylor green vortex problem. So you can see that for a strong scaling, we need to fix the problem size. So we fix our problem size to be 128 cube with this many number of nodes. The black line is the ideal speedup, meaning that if we increase the processor from 16 to 32, which is by 2, the speedup will also be 2. Instead of taking 100 seconds, it will take only 50 seconds. Okay, that is very ideal. We will not be able to get it. What we get is a small deviation. It's not very small. We have deviation from the ideal speedup curve, and for 64 cores, which is the maximum we have tested, the speedup is only 0.625 instead of 1. Okay, ideally it should be 1, but we get a 0.625, and but this is not as bad as it seems, because the Ahmed law says that the maximum speedup is 1 by F, where F is the serial fraction of the code, meaning that even if you increase the number of processes to infinity, you will not, your computational time will not approach 0. Okay, that is because of the serial fraction of the code and how strong scaling works. Okay, a better measure of the parallelizability is weak scaling, in which we increase the resource, meaning the number of processors, and we simultaneously increase the problem size. Okay, that I'll show now, and this is governed by Gustafson's law, where the speed up with processor P is proportional to F. Okay, and this is the result from the weak scaling. So again, we consider the turbulent flow problem. We started with processor 1. I think this problem size is wrong. So when we increase the number of processors, we also increase the number of nodes by 8. So when we go from 1 to 8, we also increase the number of nodes from by 8 times. And then when we move from 8 to 64, we again increase the number of nodes by 64. Okay, this data is not correct. Okay, so ideally the efficiency should be 1, but we get a value of 0.81, which is good enough, because we have made sure that our code is parallel as well as it is readable. Okay, you can lose the readability and increase the parallel efficiency, but which is not something we don't want to do. We want to maintain the code, and when new students join, they should be able to follow the code. Okay, so this says that our code is moderately doing well in terms of parallelization. Okay, so I'll briefly talk about. So until now, the results I have presented are for single phase flow. I will briefly talk about two-phase flows. So in addition to the momentum and the general pressure equation, we also need to solve for volume fraction. By volume fraction, we mean there are two fluids in the domain now. So volume fraction says at a given point, what is the ratio of volume of one fluid to the volume of the other fluid. Okay, so these are the technical details of the implementation. So I'll show two examples. The first one is a bubble race problem, where the surface tension is important. This is a challenging test case because the density ratio between the two fluids and the viscosity ratio are very high. Okay, so the density ratio is 1000 and viscosity ratio is 100. Under such large ratios, having a stable computation is challenging, but I'll play the animation again. You can see that the initially circular droplet takes a very complex shape with even a small, almost a breakup here. And the accuracy is quantified by plotting the velocity of the droplet against time. You can see that the red one, which is from our simulations, are matching very well with the reference results. Okay, and I will conclude the two-phase flow by simulating a three-dimensional problem where there are two fluids which is separated by this interface. Where this blue one shows the shape of the interface, and because of the density ratio, the flow becomes unstable and the interface evolves into a complex phase, as you can see from here. Okay, so initially a slightly curved interface becomes takes this complicated shape, and the accuracy of the simulation is quantified by the location of these 3 points from the initial condition: bubble, spike, and saddle. As you can see that our results matches very well with the existing data. Okay, so before concluding, I will spend only one slide on GPU parallelization. So our code runs only on CPU, the one that whatever I have discussed now. We wanted to port our code to GPU, and we had this wonderful opportunity to attend the GPU hackathon, which was organized by NSM at IIT Bombay. Within just 2 weeks of time, we are able to port our code from a serial to GPU using this open ACC. You can see that for a 64 cube mesh, we have got a speed up of 10, which is not impressive, but this is a very good result considering the amount of time we have spent. Okay, there is a lot of work to do on GPU parallelization, and I would like to mention Dr. Sharad and Mr. Kuvelkar that we are very much looking forward to the next edition of this hackathon. Okay, so that brings me to the conclusion. So what I have presented is a solver based on general pressure equation. It is accurate and it is portable to parallel computer architecture, and it can be considered as a potential alternative to lattice Boltzmann method, which is another method that is highly that can be highly parallelized. And our future work is to extend it to unstructured grids and multi GPUs. So before finishing my talk, I'll thank the students who worked on this. So Dheeraj is a PhD student. So he's the one who started developing the solver from scratch and did the complete CPU parallelization, the MPA parallelization, and he's the one who is leading the GPU parallelization now. And Hormuz is a junior research fellow who is the one who has developed the two-phase flow solver. Okay, and that's me, and this is my email ID. If you have any questions, I'll be happy to take now, and feel free to write to me also later. Thank you.
Thank you, Sudhakar. So any questions from the audience?
Sir, one request, sir. Can you move to the first case where you have introduced the artificial compressibility?
Yeah, sure.
Sir, is it
you're
somewhat
talking about this one?
Yes, sir. Before this one.
This is you are talking about the challenges slide. This one or the next one?
Next one.
Okay, yeah, this one. Yes.
Sir, is this somewhat close to pressure correction method?
No, this is not a pressure correction method. So all the pressure correction method requires you to solve an elliptic pressure equation, right?
Yes, sir.
So this is close to a penalty method. So we are introducing a penalty parameter here, which is the artificial compressibility parameter. And when this parameter is very large, then we are going to satisfy this equation. So it's close to a penalty method.
Sir, that means if we have, say, for example, initially we have the pressure values, then we can solve the momentum equation. With the momentum equation, then we solve the second equation. So like that, iteration goes on, isn't it, sir?
Right. So So computationally, from HPC point of view, explicit time integration is very good. It is easy to parallelize, right? And they have it is highly the algorithm itself is highly parallel.
Okay, sir.
But if you go for the classical pressure correction or the simple type family of methods, you will solve this pressure correction equation. The same form will be the pressure correction will also take the same form, right?
Yes, sir.
So
yes,
we
sir.
don't have a time derivative of pressure here, so we cannot use the explicit time integration. So all the matrix vector product assembling things into matrix, all those things will come into picture. But here we have introduced a pressure derivative, which means that we can use explicit time integration for both.
Yes, sir. Yes, sir. Yes, sir.
Yes, yes.
Sir, so that means now you have parallelized the used parallel for solving the momentum equation, and then for this artificial compressibility equation.
Yes,
So,
yes. Both are parallel. So first, this equation is solved in parallel. Let's say if we use 256 cores, all the 256 cores on the cluster will work to solve this problem, this equation, and then all the 256 cores will work to solve this this equation. Yeah, yeah.
Sir, one question, sir, whether
yes, yes, please. Okay. Am I connected?
Yeah, you are connected. I think you
okay.
are.
Okay. All right.
So in the meantime, this code that that your students have developed,
yes.
Is it also publicly available or?
It is not yet. We would like to make it public after making some changes. It is not yet publicly available.
But do you have any references of, say, publicly available code of a similar type that the participants can look at?
So parallel artificial compressibility solver we are not aware of. There are many solvers, for example, OpenFOAM that solves the classical method. But with respect to artificial compressibility method, we are not very sure. To my knowledge, such an open source solver is not available.
Okay. Any other question from the audience? Fine.
Look,
then
yeah.
Then we will. Then thanks, Sudhakar, for this talk. And it is interesting to see that we are also developing a solver that maybe sometime in the future we will release in the open source.
Yes, yes.
And try.
Yeah. Okay. Okay. Thank you, Sharad.
Yeah. So we will move on to the next session for the day. So the next session is on National Supercomputing Mission. Because this workshop is being organized and supported by the National Supercomputing Mission, which is a mission of the Government of India under the Ministry of Electronics and IT. We felt it would be good for the participants to know more about NSM and what different kinds of activities NSM supports, what kind of resources NSM has created in the country, so that you are more aware of how you can benefit from this national mission. So this session will again be conducted by Mr. Ashish Kuvelkar, and as I have mentioned earlier, he is the head of an NSM HR group, so he is the best person to talk to you about this initiative of the government, especially from the education and training point of view. So over to you, Ashish ji.
Am I audible?
Yes, yes.
Okay. And the slide is visible, I hope.
Yes, it is.
Okay. Okay. So, good afternoon. In this session, I would be talking to you about the overview of the National Supercomputing Mission. So, this mission is essentially a mission of Government of India with Department of Science and Technology as well as Ministry of Electronics and IT. These are the ministries which are driving it, and ISC Bangalore and CDAC are the implementing agencies. So let us see what is that the mission tries to achieve. As already mentioned, it's a joint initiative of METI and DST, and the total outlay of this mission is 4,500 crores. This mission is of duration 7 years, and it's going to end formally on 31st March 2024. That's we are left with 1 year of it, and as a you will see what the progress has been over the past 6 years. The key deliverables of this mission includes first is it's basically meant to develop a capacity as well as capability in the area of high performance computing. So as a result, there are four main verticals in which this mission is operating. So the first one is setting up of NSM or HPC facilities and infrastructure. Second one is developing ab initio development of HPC applications in the area of in 5 major areas which are of special interest to the country. Then we have one vertical that deals with the research and development during this time of mission, so that in the next version of the of NSM, the country would like to go in for exascale computing. So as I mentioned in my first lecture, the world has seen the first exascale computer, and India would also like to have one. So in that respect, whatever are the building blocks required, their initial design or testing can be done during this mission. And as Professor Sharad mentioned, one of the verticals is about the human resource development, where we are trying to uh, have about 20,000 HPC professionals who would be who would support this mission and the HPC activities in the country in the future. So coming to the supercomputing infrastructure, the first one. So this basic aim is to build supercomputing facilities, and I'll cover that in the slides to come. However, this has been divided, a three-phase approach has been taken. So when the mission began, we tried to take bought-out items. That means the systems were assembled in India, which means that the basic components like nodes, in the morning I told you what are the basic components. The nodes, the switches, the software. So most of it was, especially the nodes, which form the heart of the supercomputing systems, they were assembled in India, whereas the components were sourced from abroad, but they was assembled in India. In the next phase, what we said was the supplier was told to manufacture the boards in India. That means the entire nodes, they were, of course, the components, there is no fab in India, so all the silicon components have to come from abroad. But the PCBs were assembled, that is putting the components in the PCB, soldering them, putting them in the mechanical chassis. All these things was manufactured in India. So as a result, what happened was the ability or the capability to manufacture high-end printed circuit boards that got established in India. Whereas in the third phase, which is currently on, the board, especially the important things like the server motherboard and and the network interface card, they have been designed by CDAC. And of course, as I said, the manufacturing capability already existed. So they are being manufactured in India. So now, as of now, what has happened is 15 supercomputers with a cumulative compute capability of 24 petaflop has been already established. I will give you the details in the next slide. And what's coming up in the next about 15 months would be 9 supercomputers with a compute capability of 40 petaflops. So overall, there's going to be about 64 petaflop of capability, or 16 petaflop of compute capacity would be built as a part of this national supercomputing mission in 7 years. So these are the some of the supercomputers that have already been set up. The first three, as I said, in the phase one, that is assembled in India. So in assembled in India, there were the first one was set up at IIT BHU, Param Shivai, and that had a compute capability of 833 teraflops. It was inaugurated by Honorable Prime Minister Shri Narendra Modi in 2019. Then came one called Param Shakti at IIT Kharagpur with a compute capability of 1.66 petaflops. The third one, Param Brahma, was installed at IISER, Pune, which initially had a capacity of 797 teraflop, which was augmented with almost 1 petaflop. Then IIT Kanpur had got Param Sanganak, JNCSR had this Param Yukti, and IIT Hyderabad got 833 teraflops. So this got completed, IIT Kanpur, JNCSR and IIT Hyderabad, just after COVID. So there was some gap of about a year or so. But these systems were phase one systems, and the phase two systems were, as I mentioned, they were like assembled in India, Nabi Mohali, and that's Param Smriti, then NIT Tichi, Param Porul, and at CDAC Bangalore, we had Param Utkarsh. And the last three systems of the 9 systems, that is phase 2 systems, is IIT Mandi, Param Himalaya, then IIT Gandhinagar, and IIT, there is one at IITG is IIT Guwahati and IIT Gandhinagar. So these 9 systems have been installed, and as a result of this, one more system which was at Pune, it's called as Param Siddhi AI. That's currently the #1 system in India, and it has a compute capability of 5.26 petaflop. However, it also has got a complete AI stack, and if you look at the AI petaflop, so what happens is HPC petaflop, I mean HPC's compute capability is calculated in terms of the floating point operations it can give, whereas in case of AI, since it is used more for training and similar purposes, you don't use double precision floating point. Instead, you use single precision, and as a result, the compute capability increases much more, because the CPU is able to perform a lot more AI operations than the floating point double precision operations which are required for HPC. So that's why it's mentioned as 210 AI petaflops. And when it was launched in 2020, it was ranked at number 62 position. And this is a platform that allows both HPC as well as AI workloads to be run on it. And 377 users from 25 institutes across the country are using it 24/7, out of which National Language Technology Mission called Bhashini. Here the aim is to have a seamless translation between 22 Indian languages. It's a project of METI for which it is being used in a major manner. Now this is a roadmap that shows how we are going to go for exascale. So some of the things I will keep mentioning in the upcoming slides, whereas let me just put my cursor in the pointer. So here I mentioned these systems that have been installed. Now parallelly we are also, I will talk in the coming slides about the design aspect, phase 3. So we already have this Rudra server boards and Trinetra boards, and the work on Om processor, that's the indigenously developed ARM based processor, that work has also started. So this half you saw that some of these systems have already been installed, and in the phase 3 we are going to get systems at IIT Bombay, IIT Madras, IIT Delhi. So these systems are going to come, and this based on Om processor we are going to get this Paramanant, and because based on the processor we will be designing a similar server based boards that are seen here. And we are also, as I mentioned, the Trinetra's 200G gigabits per second network is currently being developed, and the boards, basically three things we are doing. We are developing the motherboards, and currently they are being developed using Cascade Lake processor, and the next one is going to be using Sapphire Rapid. So these are the processors, Xeon processors that Intel makes, and so we make motherboards, we make network interface card. The Trinetra A, which was 100G, is already functional, and it has been proved in, as I will show you some pictures, in a cluster. And then next one is going to be Trinetra B, which will run at 200 gigabits per second. So this is going to come by the end of the year. So that's the second aspect. And the third aspect is processor. So if you have developed a processor, we will also make a motherboard around that. Then we will also have a network and the motherboard combination, and there will be I had in the morning I had mentioned to you about parallel file system. So the caching part of it, the using solid state drives, is what we will be making at the end of this year. So we have storage, we have processor, which will come next year or beyond that, and the network interface card, and that will make I mean, going a couple of years down the line, we will have the complete supercomputing system with most of the building blocks being made in India, which gels well with the Atmanirbhar Bharat concept that government has proposed. So till now, now you have this entire range of computing systems that I have mentioned to you. So what are the things that are available on it? So there are the various HPC applications, starting with bioinformatics, then molecular dynamics, quantum chemistry and material modeling, computational fluid dynamics. Professor Sudhakar mentioned one such code that he has developed on his own. But all of these are open source softwares that are available, like for weather and ocean disaster management. Anuga is an open source code which CDAC is adopting. Now, running applications have to be supplemented by visualizations, which take the input data from that this code has generated and show the data in a meaningful form. And there are libraries and programming models, some of which I mentioned in the morning. So this relates to the top half, relates to HPC, whereas now, as I mentioned, there is always dual use of an HPC system, where one can use it for applications related to AI, machine learning, deep learning, etc. So TensorFlow, NumPy, Nroot, Jupyter Hub. So all these commonly used frameworks and integrated development environment, they are all available on these NSM systems. So now we will look at the next part, that is the R&D part, wherein we are taking an approach to build the systems in India. So here are the details for the same. So I mentioned to you there are two things that we are doing. One is a Rudra server and other is the network interface card. So this shows the PCB with the layout, and you would, once it is populated, it looks like this. In the morning I had shown you a similar diagram wherein there was a dual socket processor board. Now the good thing about this is that this is in a form wherein in one U body of the node, you can put multiple such boards. So each one of them will go inside, and the depth, this is the depth of the rack, and multiple such units put one next to another will make the width of the rack. So this is based on Cascade Lake, and as I mentioned, the one used based on Sapphire Rapid, that is a third generation Xeon processor that is going to come soon. So this is actually a board that has been is being manufactured in India. Then Trinetra, as I mentioned, A with 100 Gbps, that is already available here as is seen in the picture. The next version of this, called as Trinetra B, which uses torus as a topology, that is being developed, and by the end of the year that network interface card would be available. This is to be supplemented by the software stack. I will show some details about it later. So that has been developed. So it's like the processor is bought out, but the motherboard and the network is designed by CDAC. The stack is designed by CDAC, and as a next step, an HPC processor called OHM, based on ARM HPC extensions licensed by CDAC, would be developed. And when you have that processor and boards built around that, the total content, indigenous content, would be going to be 90%, which is designed in India, manufactured in India, and other components like memory, etc., which are not made in India, they will have to anyway be imported. So here the assemble board, Rudra board, looks like this. So you will notice that there are two versions, one which is 1U height, and this is double the height. So what is the difference between the two? The difference is that this can additionally take accelerator cards. So remember, in the morning I had said that you have some compute nodes without, they are only CPU based, some are CPU plus GPU based. Bharat told you how the CUDA architecture works. So this board is capable of taking two such GPU cards. So of course the GPU cards will come from Nvidia or any such vendor, but you can see that in a 2U rack you can fit 4 such boards. So this is called as a brick, and what you see here is the power supply, and these cables, they are for Ethernet, and similarly from the back side of this you will have the paramnet connectivity. So you can put a paramnet card here, and that will allow many such nodes to be connected. So this motherboard is called Rudra, and the proof of concept having 4 GPU nodes and 2 numbers of A100 GPU cards. This has been tested, and I mentioned to you top 500. That's a worldwide list in which Param Siddhi AI was at rank 62. Similarly, there is a top supercomputers of India. This list is generated by IISc and CDAC. So in that we had an entry for this 4-node cluster, which could have a peak compute performance of 126 teraflops, and from which LinPack performance was 94.63. So this made it go into the list of top supercomputers in India. Moving ahead, this is a roadmap for Rudra. Like as I mentioned, the one with Cascade Lake is available today. And this picture that you see here is based on Cascade Lake. Intel has just announced Sapphire Rapid processor. So you will notice that it will have each node will have a peak compute power being going from 3.68 to 8.32 teraflops, and this will also have support for 4 GPUs. So this board is in design of this is in progress, and once we get the home processor, we will have the Rudra, which will be based, which will be called as Ananta, and that will be based, that will give even further more compute power of 10 teraflop per node. So this gives the pictures of Trinetra. So this is the board that I showed in the previous one. This is the Trinetra A, and this is the Trinetra B, which we will see at the end of this year. And this will have Trinetra B will have a link speed of 200 gigabits per second. The Trinetra A has a link speed of 100 gigabits per second. So we have to go in steps. So as and when the FPGA and other technologies they improve, we are going to get better and better networks. So this has been put in as a Trinetra A has been put up in a network, and once the network is designed, we need to test it. So how do you test a network? By making a cluster out of it. So we have these standard nodes in which we put the Trinetra A card, and the next step is put the stack on it, the software stack on it, and run benchmarks. And like Intel MPI benchmark is one of the standard. Similarly, you take the application codes, standard open source application codes, and run on it. And as a result, as I mentioned to you earlier, it has entered the top supercomputing list of top supercomputers in India. And we intend to build a bigger cluster, 32 node cluster, which will further test the system, and we will be able to fix the bugs if any. So it's like a work in progress. So this in the morning also I had told you that you have OS, middleware, and HPC programming tools. So like what is mentioned on the left hand side are the ones that are open source or given by manufacturers like Intel and AMD. However, CDAC is also making its own contribution at every level. So that is what is written here, that you have a cluster. Some of these are script based, some of them are web based, some of them are a combination of some some clients that run on every system, and aggregator that runs on another system. So let me show you one such product called as C-Chakshu. So this is a multi-cluster monitoring tool. Remember, I had told you for one system, there is a monitoring tool that can be running on one system, and you like ParaView, or there are other tools which help you in monitoring the performance or seeing the status of which nodes are up, which nodes are down. So similarly here, we have developed this centralized multi-cluster, meaning that all the 9 systems that I told you that have been installed, we have at CDAC Pune one central facility wherein you get such reports and you get such alerts which help you in knowing what are the number of applications, who are the users, how many codes are running currently, what is the performance that the system is offering, what is the idle time, what is the wait time in a queue. So all these things plus such reports over a period of time. Like here it says that 30% of Param Shakti was used for codes related to computational physics. 18% were used by codes that are of type computational fluid dynamics. So sitting at one place, the system admin team can monitor and they are able to support the users. So this also contains ticketing system. So what is a ticket? Like you are a user of the system and you are facing some problem. Maybe the compiler is giving error that the current version of library that is being installed is not being supported by the compiler, or the code that you have written needs to use an older version of the library. So the user will use a ticket. So it's like a reaching out to the customer support and explaining your problem. And then there are a set of people, just like you have, let's say you face some problem with your mobile phone vendor, you call their helpline. So it's a direct interaction between the user and the supervisor or those who are attending to problem. Here it is more like mail based, because what happens if the problem is reported, the problem has to be replicated, then a solution or a workaround has to be found out and then informed to the user. So like we have thousands of users who are using these systems, and we have dedicated team of system support engineers who are handling it through a ticketing system. And as I mentioned, you can have a history of usage and the problems faced, the uptime, etc. And this can also, there also contains application profiling, which can give live feedback to the user as to what is the efficiency of the code that he has written. Then there are other tools that our Bangalore team has developed, which includes automatic parallelizing compiler. So if you have a sequential code and you need to target it to a particular param system, then you would be able to use this parallelization tool to convert that code, and it will look for certain patterns, and then it can be targeted towards a particular hardware. Just like you have Jupyter Notebook, or you have integrated development environment for various CPUs, parallel development environment called Parade has been developed, which allows hybrid parallel application development. When we say hybrid, what we mean is that the one that is can be used for CPU plus GPUs. So you have to write the code in and inform the compiler through compiler directives as to which part of the code is tuned for CPU running on CPU and which part is tuned for running on the GPU. Then similarly, we have HPC cluster utilities, which what they do is essentially, if at some point in time, suppose there are 500 nodes, out of which 20 or 30 are not being used because the load is not much, then they will go into sort of hibernation, which will conserve power. But whenever some job is ready to run and those nodes are assigned, they will wake up and immediately start running the job. When you are writing a parallel code, it is important to identify the hotspots. So what is a hotspot? Hotspot is the routine or part of your code or a module in your code that is taking a lot of time to run. So when you identify the hotspot and find that a particular part is taking too much time to run, you would be naturally inclined towards optimizing that, because the one that takes largest amount of time, if that can be speeded up, the overall code running time will come down. So a profiler is a kind of a code that helps you to do a parallel profiling of the parallel code, such that you can see where there is a bottleneck. Many times the bottleneck is communication, in which case you need to modify your algorithm to make sure that there is a good balance between computing and communication. One more thing, as a part of R&D that CDAC and IIT Bombay has developed, is what is called as DCLC, means direct chip liquid cooling. So what is chip cooler that you see here, the processor is beneath this, and as you know, when the processor runs at a very high speed, it generates heat, and normally you put a heat sink with a fan which will extract the heat and dissipate it to the air. When you have a convection cooling, which means air takes away the heat from the source of the heat like a processor, it is not all that efficient. You can, I mean, try to imagine this. You have, let's say in your kitchen, you have heated a vessel full of milk, and suppose you want to cool it faster. If you leave it to the, if you just keep it on a table, it will follow Newton's cooling law and it will take certain time, maybe 20 minutes, 30 minutes to cool down to room temperature. But just imagine this, you have another bigger vessel full of water and you put the vessel containing hot milk, hot vessel of milk in that water. You will find that the water will get heated faster and the milk vessel will cool down faster. So exactly same thing happens here. These tubes contain flowing water and there is this water is taken to an external facility where through the adiabatic cooling, this cooler will take away the heat. And this is not for just one CPU, but every motherboard will have two such CPUs and a rack will have multiple such nodes, and there will be a loop that is formed out of this, and each CPU is capable, each cooler is capable of taking 360 watt of heat, and the panel will be able to take a cumulative sum of many such chip coolers, which comes to 30 kilowatts of panel exchange heater, which will be taking off the heat of inside a rack. There will be multiple such chip coolers and a loop will be formed among them, and flowing water will, hot water will be brought here, it will be cooled and it will be pumped through this. So cold water pumped through this, or water at room temperature pumped to this, will extract the heat from the chip. So the third part is about the HR development activities. So as I mentioned to you, the target is to develop 20,000 HPC manpower, and CDAC alone is not doing it. It is doing in collaboration with academia and industry. The 4 nodal centers at IIT Goa, IIT Kharagpur, IIT Madras and IIT Palakkad is one such effort. And this program, today's lectures, today's training program is coming to you through IIT Goa's nodal center. Similarly, you saw Bharat delivering a lecture. He's from Nvidia. Similarly, we have members from Intel, whose products we are using to deliver talks on their products, software products that work with the HPC hardware that we deliver. Then we conduct training programs. They are meant for faculty development. They are meant for students of undergraduate and postgraduates. There are workshops. The boot camps lead to hackathon. Professor Sudhakar mentioned that the code that they were developing was brought to one such GPU hackathon, and as a result there was a increase in the performance. So it's a mix of various kinds of training programs that that help in developing the capability in HPC aware manpower, and that's the overall aim of this vertical. And to be able to like today morning there was a discussion about the professor wanted to teach these concepts to their students. So we have developed a model curriculum which is available for free. Anybody can take it and adopt it for the running course in their college. Then we had conducted online courses on HPC, ML and DL, and one of these courses is available in NPTEL, as maybe again it will be run. It was run once and we had a very good response, and it's as a result it's going to be run again in the month of June. Possibly we will have the HPC course also available there. Then through the efforts of Government of India, we have training programs specially for SC/ST candidates which are free of cost, and about this, the figure is older. Till now about 18,000 students, researchers and faculties have been trained. So that was about the about the training aspect, and as we mentioned in the morning, that we plan to have a face-to-face workshop at NIT Arunachal Pradesh in a couple of months from now. The last part is about application projects. So as I mentioned, there are 5 applications that have been developed. So I will explain them one by one. Here is the list. So first one is about genomics and drug discovery. And again, you will find that each of these project is CDAC is the lead agency. However, we are collaborating with various national institutes where we get the domain expertise, and CDAC provides the computational expertise. So I'll explain each of these 5 ones one after another. So this is a development of entire platform which will be used by the bioinformatics community, sorry. And there are specialized, like I mentioned to you, various NSM infrastructure setups that are made at various institutes. Apart from that, dedicated facilities have been established. 2 dedicated facilities have been established at CDAC Pune. One is about the big data cluster, wherein large amount of data processing can be done very efficiently. These nodes have got large amount of memory, which helps in speeding up of this sequence search and other things. Then there is a facility where you run applications related to bioinformatics, which, and if you notice here, what is mentioned here is a pipeline. So what is a pipeline? It is a workflow. That means that it's not just one program, but there are multiple applications in a pipeline, such that output of first application serves as an input to the second application. And the aim is that the pharmaceutical industries and others can use this pipeline to discover new drugs. Or another thing that this helps is what is called as drug repurposing. Like you might have heard about this during COVID, we had remdesivir as one of the potential drugs. So how was that done? Remdesivir already existed. It was not a drug that was made for COVID, but that was a existing drug was repurposed by checking its affinity towards destroying the corona or SARS-CoV-2 virus. So that is a drug discovery. Similarly, another pipeline is for genomics. So what is genomics? That is useful to do a genome sequencing of an individual. And looking at the genome sequence, one can find out, or the doctors can find out, whether a particular person is susceptible to some kind of diseases. Because you may be aware that some of the diseases are hereditary, like diabetes. Some versions of diabetes are hereditary. So checking that out and early detection of that. And if you have, let's say, affinity towards a particular disease, then one can be watchful for it. Another thing that genomics helps is personalized medicine. Today what happens is, if 10 patients go to a doctor saying that they have cold, the doctor will give the same set of medicine for generic cold that he gives. However, if he has this personalized genomic data, if there are 4 ways of treating cold, he will try and check which one of them would be most suitable for him. So to be able to do this, genome sequence is important, and that further leads to alignment, sequence assembly, calling of the variant, and checking all these things. So again, this is a pipeline where the output of one serves as an input to other, and finally your aim is to figure out whether a person has got affinity towards certain disease, or which kind of possibly available drugs will best suit him. So for all this, we have a team of about 50 persons, both computational expert as well as domain experts, who together work towards development of this application. And then this shows the societal impact of that work. That and let me also tell you that this team is not only working on human health, but in conjunction with University of Surrey, team is also working of health of livestock, because what applies to us as human beings applies to other animals as well. So and not only that, there is a team that is working on agriculture, because if you have animal genomes, similarly you have plant genomes, and the things that I mentioned about human beings applies to animals as well as plants. So that this has got quite a wide reach of targeted use, not only in for humans but for veterinary as well as agriculture. Another application that is being developed is about urban modeling, that falls in the category of weather and climate, and this involves a coupled model, because you cannot take rainfall in isolation or humidity in isolation or winds in isolation. They are all coupled, and with so much of pollution coming in, one needs to find out how that's going to affect human lives. So the weather coupled with things related to uh, uh, things like pollution, what are the sources of pollution, vehicle pollution, and how it is affecting urban air, how it is affecting rural air. All this is being done in a integrated manner. So that is what it does, that there is a database, there is a live input of data related to weather, related to satellite imagery, related to things like earthquakes or tsunamis. So all these things are put together, and there are some things that go to the government agencies like IMD. There is something that goes to the citizens who can use this a mobile app to know how the weather is going to be, or it can also go to the disaster management authorities to predict such extreme weathers or inundation or anything that is going to affect human life and property. Another specific aspect of this, what I mentioned earlier, is early warning system for flood prediction. Now you are very much aware how floods happen, that upstream there is rain, the rain gets into a river, there are multiple tributaries of the river, depending upon where the rain has fallen or cloud burst has happened, the water flows, and water flows at certain rate, and it flows through valley of a river, or there are plain areas that is goes through. So all this digital elevation model of this area in and around the river, like this what you see in the picture is for river Mahanadi, and you know that there is a Hirakud Dam on river Mahanadi. You also would be aware that if there is lot of rain upstream of that dam, then the dam collects water, and the dam has a particular capacity. Beyond that, the doors have to be opened. Now, if the doors are opened at a certain opening, the discharge will depend upon that, and depending upon the discharge, the water level is going to rise. So all these things based on forecasted weather and the digital elevation model helps us in developing an early warning system, which will help the national disaster management authorities to evacuate people, to allow them to take their belongings with them. If an early warning is given, you can limit the damage that is caused. You may be able to save lives. You may not be able to save property. If there is too much of rain and the water level rises and it breaches the bunds across, then nothing much can be done, but at least you can protect the lives of people, and that is what this tries to achieve. Then there is another project which is about seismic modeling. So what is that? What happens is this is useful for knowing the reserves of gas and oil beneath the earth. So you send artificial waves, they get reflected, you measure them, which applies to land as well as ocean, and then you do a 2D or 3D migration of this real-time data, and you create a patterns, and the patterns will tell you whether there are reserves uh, beneath the earth. The last one, a team is working on. See, what happens is many of these applications are legacy, like WRF. This code was written about 40 years ago, and as the architectures evolve, the hardware architectures evolve, you need to port these applications across, and there is a team that is working on various applications, and users are writing applications, and students are developing new codes, and if they have to be, or open source applications have to be optimized for the architecture that's coming up. Some of them would like to scale it up to more number of nodes. So all this is done through this team. So point we are trying to make here is not only you are developing new application, even legacy applications are being ported. If the users are modifying those applications and if they're facing any issues, so they are being optimized through a team of dedicated people, just like we have team of people handling the ticketing system. Similarly, we have a team of people who are hand holding the users. So that in gives, I'm sure you would have got an overall idea about what we are doing under NSM. What I would like to also tell you is that these systems are available for anybody to use. In case you have a requirement, you are a parallel programmer and you would like to use the system, do get in touch with me. I had told my email address in the morning. Unfortunately, it's not written here, but it is ashishk@cdac.in, ashishk@cdac.in, and I will put you across to the right person who can help you in getting an account on one of these systems. There is a formality to be done in terms of getting authorization from your head of the institute and telling what you are going to use the system for. So free access to the system is available. So with that, I am open to questions. We have 5 minutes for taking questions if you have any.
So I have one question.
Yes.
This Nesra art Mudra servers that are being developed. So will they be launched in the market by CDAC, or would they be finally taken over by some other company?
Right. So what happens is even as I mentioned in phase 3, we are going to need about 2000 such nodes, and these are very specialized ones, and you need precision equipment to assemble them. And there are some 3 or 4 companies in India who have this technology to manufacture this board. So there is one company by name VVDN. There is another company by name Sanmina. So these are like multinationals who have their setup in India, and we are manufacturing. We are already tied up with them, and the boards that we need they will make and give it to us. They will be supplied to NSM system. We have also given them license, royalty based license, that they will make these boards in and sell these as nodes in the market. And the good thing about this is that, I mean, I'm not sure whether you remember, but some time ago there was a case where the BIOS on one of the nodes that was made in China, there was a suspicion that some of the data that it is collecting from the nodes, I mean, the computer systems that is running some codes, it was secretly passing out to some outside the country. So now any such board that you buy, I mean, even if it's made in India, but the BIOS is essentially made by some, there are 3 or 4 companies that make it. So what we have done is we have taken the royalty for the base BIOS, and we have modified it. It's called as BMC, Board Management Controller. So it's a board management software, BMS, and that runs on every motherboard. So that is entirely developed by CDAC. So many of the security agencies like NTRO National or NatGrid, they are looking forward to using these systems as because many of this is, or you can make a cloud out of them. So there are various applications, because finally it is a multi socket node that is the basic building block of any server. So that is the reason why CDAC has made this, because apart from HPC, it can be used for as a general purpose server as well. Only thing is that brick part may have to be relayed in a different way, because there you need more number of hard disks and other, I mean the architecture of the node becomes slightly different. So we are tuning it for the other applications as well. So it will be available.
Okay. Any other question from the audience?
Hello, Mr. Kuvelkar. Good afternoon.
Yes, good afternoon.
So what do we mean by porting a code to an exascale architecture? Let us say we have a code, let's say MPI code, which is highly optimized for the current architecture.
Right.
If I just move the code to an exascale machine, will it run with the exascale scale speed?
Right. So there are two aspects in this. The first aspect is that if the same environment is available on the target or the bigger system, and the code is scalable, in the sense that you have got you just rewrite the configuration file saying that currently it was using some say 16 nodes, there use 32 or whatever, it was using 256, use 1024 nodes. If it's scalable, then it will work. I mean, as you said, it will give a better performance. However, what happens is that with the newer systems, some of the CPUs would let's say the one that you optimized it for earlier had 32 cores. Now the new architecture, let's say, comes with 96 core processor. Then the cache memory is higher. Then the number of the kind of network that is different. I mean, it has got more bandwidth. So some tweaking is needed, wherein what happens is, like, you may be using the shared the model that you are using may be a combination of OpenMP and MPI. Now there some tweaking may be needed. So basically, it is when I say porting, it could mean that recompilation with the newer, let's say, Intel Studio version changes. Then some things may change, or it will try to make use of the underlying hardware in a better way. So that's where sometimes there are errors that needs to be fixed, because there is there's maybe incompatibility issue with the APIs or the libraries, something like that. The calls that you make, that is one aspect. Other is it runs correctly, it gives you the right results, but there is a scope for running it faster, because currently, let's say, it is using only 32 cores out of the 64 that are available, because that's the way it was designed. So that's what is meant for what I meant by porting and optimization.
Okay, thank you very much.
Yeah.
Sir.
Yes.
Sir, not at a large scale. Sir, can we take this to our UG and PG students, sir, and of course research scholars? So is CDAC open to only high-end research, or
no? See, what happens is, for user for training purpose, as I mentioned in the morning, one of the systems will be made available to you. So we have to decide how many number of students, what is their level, what are they being taught, and a system will be made available to you. Because we have some systems which are dedicated for training purpose, a smaller system, because they don't want to scale up their code to, let's say, 50 nodes, 60 nodes. Even a 4-node, 8-node system is good enough for them to prove their concept. But if it's a research scholar who has done this aspect, and wants to try it on maybe something like 64 nodes, 128 nodes, then we have another set of systems that can be used. So depending upon what the purpose is the system being used for, we will make one available to you. So every need will be satisfied. That is the whole aim of pumping in thousands of crores of rupees of government to make something available which meets the need of everybody.
Yes, sir. Exactly, sir. Sir, I am really sorry. So, lot of things appears too technical for me. I am a math professor, sir.
Okay.
Sir, what I want is I want to increment my, say, for example, I am handling numerical methods. Now,
Yes.
even maths is going to be more symbolic. So, I have introducing symbolic computations also. Now, slowly, I want to leverage this benefit of CDAC. So I will slowly change my or increment my syllabus, implementing this parallel algorithm using CDAC, so that the students in general get familiarized. So that is my idea, sir. So for that, whether the systems will be available through cloud for that, so that students can anytime work on it.
Right.
Yes.
It will be available. It will be available. Only thing is that we need to train them initially to how to make use of it. Okay.
Yes, sir. Yes,
So
sir.
as Professor Sudhakar mentioned that if you have just a serial code, then you need to put in efforts to make it parallel. In his case, it was a dedicated core for a specific purpose. However, in your case, we would be doing it in a generic way. That is, we would be teaching the techniques of how to write parallel codes, and anything is what is important is application of this to a domain. Like CFD is what Professor Sudhakar's is, mathematics is what yours is. So you may be developing some generic techniques which can be used by other domain experts. So I'm not conversant with what branch of mathematics you deal with, but there could be things like statistics or I'm something like that, or Jacobian methods or something which needs large number of computations are in such a way that you can parallelize them. So you are the ones who can tell us, people like you can tell us from your domain what are the algorithms that are parallelizable, and then that can be taken forward.
Yes, yes, in general, I also deal with CFD and partial differential equations.
Okay, yeah, right. So partial differential equation solvers are available on HPC, but however, you can always tweak them. You can always find better ways of doing it. So all that is possible.
Sir, it's for Sharad, sir. Sir, whether this session is for general discussion or there will be another session for discussion.
I will take 10 minutes to cover to just present an overview on resources for research and teaching. And then after that, we can have a short 10-15 minutes of general discussion.
Okay, sir. Then I will. We can discuss during that period. Okay. Okay. Thank you, sir. Thank you, Ashish, sir. On behalf of our institute, our director, Professor Dr. Pankeshwar Mahanta, and myself, and on behalf of NIT Arunachal Pradesh. So it was really nice, sir. It was really beneficial for me, actually. So from there, of course, I have contacted Sinha, sir, last July, sir. So sir has taken his time out and planned, and we actually been successful in conducting this workshop. I am really thankful for that. So I would like to take it further, sir. So I would like all your help, and on my part also I will work on this mathematics and fluid dynamics, and of course I will try to understand the few hardwares also, so that we can implement in NIT Arunachal and we can get your expertise. We would also like to invite you to NIT Arunachal Pradesh. So this is my thanks.
Yeah, we will come. Surely we will come.
Yes, sir. Yes, sir. So it's a unique place, sir. The weather is not as in the mainland. It's completely different
So
geography.
we would like to experience that. It's
Yes,
part
sir.
of our country and we have not visited it so far.
Yes,
So
sir.
the nearest I have come to your place is Agartala and Imphal.
Okay.
So I will come to your city as well.
Yes, sir. Yes, sir. So, of course, I am inviting everybody. So thank you once again, sir. So you will be there, I think, for
Yes,
this.
I will stay. I will be around. Okay.
Yes, sir. Yes, sir.
Over to you, Professor Sharad.
Yeah, okay. So thank you, Ashish ji, for giving this overview of NSM. I think this was very helpful for all of us here to understand the scope of activities that NSM has carried out and plans to carry in the next 1 to 2 years and thereafter as well. So the next session will be a short session which I will take, and this is basically to introduce to the people here the avenues and the resources for conducting HPC research and HPC related teaching activities. So all of us here, whether we are from the industry or from academia, we understand that conferences are one of the major sources of information. Journals are there. There are also special interest groups of different professional societies like IEEE, ACM and others, which focus on HPC, including the Society of Industrial and Applied Mathematics. A lot of resources are primarily oriented for faculty and researchers, and then there are certain resources for students. So I will not present anything, instead I will show you some of these resources so that it becomes easier for you to digest. A presentation would be rather boring if I start talking about the names of conferences, etc. And then we also have domain specific resources like the work that Sudhakar presented earlier. The earliest work in that direction was published in Journal of Computational Physics. So you can think of anything computational. So computational X, where X could be biology, physics, chemistry, materials, etc. And then if you want to look for resources in that particular domain, basically domain specific journals, conferences or workshops, you can go to Google and you can find out where are these domain specific resources. I'm going to cover mostly from a general point of view so that it remains applicable to a general audience. So the first thing I wanted to show to you is this supercomputing conference. This is the world's #1 conference related to supercomputing, and it has various talks and sessions. It also has workshops and tutorials. And like any conference, you can present your research work here. But then if you have early research work where your work has made some early progress, there are some promising results, but the work hasn't matured yet, it's not in its advanced stages, then you have other things like poster presentation, doctoral showcase, research posters, etc. So there is avenue for both mature research or advanced research as well as early research but promising research. And to the participants here, I would encourage you to have a look at SC 2022, SC 2023 and look at their program and see what kind of work is being presented, what kind of research topics are being discussed, what kind of technology topics are being discussed. It will be very helpful. There are also student competitions. For example, there is a student cluster competition. This is a competition where student teams come together to design a cluster. And before I moved to IIT Goa, I was working at NTU Singapore. And in my school there in the computer science and engineering, 2 student teams had won this competition year on year, or they were in the top 3. So this is also one way of encouraging students to get familiar with supercomputing and as well as for them to get hands-on with the hardware and the software as well. Most of the time, the students would be mostly interested in software, but you can also encourage them to get involved with hardware. Then there are other programs like Mentor Pro Teach. You can see here HPC Immersion, etc., where students can team up with mentor professor and learn more about HPC. Early researchers can also team up. So if you have research students working with you, or you have masters or BTech students working with you, and this is something you would like them to explore, it's good to try it out. There are various resources, and it is just that we need time to understand what are the different resources available and then make use of it. If we spend just only a couple of minutes, then we will not be able to appreciate the the vast amount of resources that are there. So that is Supercomputing conference. Then there is a conference called HiPC or HIPC, which is the International Conference on High Performance Computing, Data and Analytics. And this is an India specific conference. Every year it is organized in India, and Mr. Ashish Kuvelkar here, he has been part of it for a very long time. So this year this is being organized in Goa in December. So here also you can present your research papers and participate in oral presentations and poster presentations. But the important thing is, especially for teachers, there is something called a workshop on education for high performance computing, which is conducted as part of the HIPC conference. It was held last year. I think this is planned to be held this year also. Again, Ashish ji is part of this as well.
Yes, it will be held. Yeah, it will be.
Yeah. So faculty members who are attending this workshop, if you are keen to learn more, you should try to attend this Edu HIPC workshop. And Goa is a nice place. You can always come here, so you can make use of the training workshops and other faculty and teaching oriented activities that will be carried out as part of this workshop. Okay. This is very India specific, and it's good to make use of it. Then there is a conference called Cluster, which is related to, again, cluster computing. And when I say cluster computing, HPC is essentially a cluster computing. So you should try to look at this also, and you will see there are various aspects related to HPC that are covered in this conference: applications, algorithms, libraries, architecture, programming, data, storage. And we went through almost all of these topics in today's workshop so far. This is also a very good conference. You can, if you have access to IEEE Explore, you can take a look at the papers that are published there. They are all providing this kind of mentoring sessions. It's not announced for this year yet, but it was done last year. So it's good to make use of it. Of course, if it is abroad, then there are some travel related challenges, but nevertheless, at least knowing about the kind of research and papers that are being published here, getting to know the research groups which are doing research related to high performance computing, looking at their websites, seeing what all they are doing. It's a good way of exploring the field and finding out an opportunity for oneself to contribute in the HPC domain. Now this is the ACM's SIG HPC, basically a special interest group on high performance computing. Again, here also there are a number of resources available. There are student travel grants. If your PhD or master's student is doing some HPC related research work and it's of a very high quality, you can nominate them for dissertation awards. If you are a woman faculty member or a scientist, either in industry or academia, and you are working in HPC, there are special initiatives for you. There are fellowships for faculty members and scientists. So there are a number of ways in which the special interest group is also trying to promote activities in HPC as well as encourage other people to join. And then of course they have their newsletters, webinars, etc., which you can take a look to find out what kind of resources they have. And then they have a lot of different kinds of prizes. I just want to mention here one prize, which is the Gordon Bell Prize, which is given away every year in the Supercomputing conference for some work done in HPC that has had a major impact in the community. The Early Career Research Awards also, the SC Conference Awards also. So that part, so awards are also there, but most importantly, our focus as scientists and faculty members and teachers, researchers, engineers is to learn more about the field and see how we can contribute. So this is some introduction to conferences and a special interest group. There are also journals. For example, this is the IEEE journal on IEEE transactions on parallel and distributed systems. So as the name suggests, this is about parallel and distributed computing, which is HPC in principle. Okay. So again, if you have access to IEEE Explore, please try to read the papers here. The survey papers are very good to understand a particular field, so you can look for survey papers published in these journals. Earlier, Ashish ji and Bharat also mentioned about accelerators, the hardware accelerators. Hardware accelerators, or accelerators for that matter, is a very broad field. It essentially means a computing device or a system that accelerates some algorithm or some software framework. It is covered in many conferences and in many kinds of journals. Accelerator related research is presented. What you have to do is you have to look for accelerator of a certain compute property. So if you are looking at GPU based accelerators, you have to look at GPU oriented conferences, GPU oriented journals. If you are looking at FPGA based accelerators, you have to look at FPGA related conferences and FPGA related journals. If you are looking at high-end processor design like multi-core processor, many-core processor, which also serve as accelerators, then you have to look at computer architecture related conferences and journals. For example, ISCA, which is the International Symposium on Computer Architecture, it talks a lot about top quality computer architecture research. So hardware accelerators is a very broad field. You have to find out which type of accelerator you are more interested in based on your interest, background, and skills, and then try to focus on that. In the morning, we also talked about top 500 list. So this is the top 500 list in front of you. Okay. If you have designed a computer and a supercomputer and you want to submit your results so that you can participate in this list or appear on this list, you can submit your results here. But it is a good way to understand how the top 500 list has evolved over the years, and you can see that the archive runs all the way from 1993 to 2022 as of now. And then there are various statistics related to these computers. So this is a nice website or a resource where you can find information about the supercomputers in the world. We also talked about the green 500 list in both Ashish ji's presentation as well as I think Bharat's presentation. So this is more from an energy efficiency point of view, because high performance computers consume a lot of power. Okay, they need continuous power supply. If power supply goes off, your normal UPS backup and all will not run for a long time. You need a dedicated power supply, which has its associated infrastructural cost. So, and these days there's a lot of emphasis on energy efficiency. And if you follow the HPC space, you might have seen that a few months back, the The top computer on this green 500 list came from Japan, from one of the labs there, and it was all built on ARM processor. ARM is also the processor architecture which CDAC is using in its own processor design. And the reason ARM processor architecture has been used for, for the top, whatever is the computer which is appearing top on this list, is because ARM is more focused on energy efficiency. It is also the processor architecture that you would see in your mobile phones. Of course, it would not appear as ARM, but it would appear as Qualcomm, Snapdragon, or something else. But the architecture of the processor comes from ARM, just the way OHM processor is being designed by licensing the ARM architecture from ARM. We also talked about Nvidia resources. So Nvidia has what they call as GTC, which is a global technology conference that is organized every year. A lot of the sessions here are free, some are of course paid, and it covers a wide range of topics, a variety of speakers, a variety of things to learn. Okay. So you can look at some of the the GTC presentations and resources that have accumulated over the years, and it will give you an idea of how Nvidia as well as GPUs are shaping the HPC community. And Bharat also mentioned about Omniverse. So this is the Nvidia Omniverse website. And the reason I have kept this particular, this particular part of the landing page is so that you can read this headline which says BMW Group rolls out Nvidia Omniverse to factories worldwide. BMW, as you all know, is a car maker. It's using Nvidia GPUs and resources under the umbrella of the Omniverse for its factories, where it manufactures cars. And you can see that there is a strong connection between the automotive work that BMW does with the HPC work that Nvidia does. So you should you can try to go through these resources in your free time and see how they can be of help to you. And this is the Omniverse channel on YouTube. Okay, so one of the videos that we were trying to look at early on during the presentation was, I think, this one, foundational technology, Omniverse foundational technology. And there are a number of resources here that you can go through to learn things. Of course, Nvidia also has a very good developer group where you can ask questions if you have any doubts and learn from them. And these are the teaching kits that Bharat mentioned early on in his presentation. So Nvidia has this Deep Learning Institute, which provides different kinds of teaching kits for different areas. For example, under their teaching kit program, they have teaching kit for accelerated computing, which talks about CUDA, MPI, OpenCL, OpenACC, basically parallel computing methods, okay, and libraries. Then if you're working on data science, you have data science related teaching kit, and of course GPUs play a role there also because of the scale of the data. So based on that, there's this teaching kit. So you can request the teaching kits. The teaching kits come with lecture slides, videos, hands-on lab coding exercises, etc. So these are some of the prominent resources that you can look at while trying to figure out what you would like to teach to your students, or what you would like to learn for yourself, and how you would like to shape your research in the HPC. Some of these resources we also list on the NSM Nodal Center at IIT Goa. So this is our website. Here we have a list of HPC related journals. This is of course a dynamic list as and when any new and good journal appears, we list them here. And these are specifically for supercomputing, distributed computing, high performance computing, cluster computing. But as I said, high performance computing also is a topic which appears in many other conferences in terms of hardware accelerators. Those we have not listed here. Those are somewhat niche. The ones that you see here are more general and broader in nature. We also maintain a list of HPC conferences. This list also gets updated as and when new conferences are announced. So for this year, we have to update it. Ashish ji also mentioned the courses that the 4 nodal centers have carried out earlier. Now, these are the 5 courses that the nodal centers have run so far. This last course, which is related to accelerated artificial intelligence, is what is available on NPTEL. We have other courses. This was our first course, which we are seeing if we can make it available through NPTEL also. So here, this course covered the basics of high performance computing. And here we had a schedule of lectures. So this schedule of lectures can also serve as a guide for you to design your own course if you want to offer to your students. And you can also see who are the people here who have contributed to these kind of topics. And if you want to involve some of them to give invited lectures or to take a couple of lectures in your course, that is also possible. And as Ashish ji also mentioned, there is a model curriculum of HPC that has been developed. That also we will be uploading on our website soon. So you can take a look at that model curriculum also to design a HPC related course for your institution, okay, or at least also to get an idea of how the basic course on HPC would look like. So that helps your own learning as well as the learning of your students. So this was all from my side, a short and quick discussion about the resources. If you have any questions, please feel free to ask.
So that was very useful, especially that last for the course related link which you shared was very useful. So probably I will go through that. Let you know.
Yeah. Okay. So what we will do now is, in the interest of time, so we have all our speakers with us here. We have Ashish ji here, Sudhakar here. I think Bharat is also there. So yeah, he's there. So if you have any questions for any of the speakers, any of the presenters, please ask your question. This is an open discussion session for about 10-15 minutes. So if you have anything, please feel free to raise your point.
Sir, actually this I think I have asked, but this is maybe for Ashish sir. Sir, you mentioned a lot of projects like urban planning and flood control, then of course COVID related also. So how to get involved in those projects, sir? So is there any lead to it, or whether we need to go through the rigorous process of submitting the proposal, for which we don't have the expertise right now, but we can start at a smaller level, smaller scale. We can start, and later on we would like to go at a larger scale. So how will you guide us through? We want to get involved. NIT Arunachal Pradesh also want to get involved in those. This region is prone to floods, deforestation, of course, prone to climate change. Yeah.
Okay, so the answer is as follows. Uh, for the current, for the applications that are mentioned, they are, let's say, like in the final stage of completion because they started about 7 years ago, and that soon there may be, maybe in a year's time or so, they may start work on the next set of such applications where there will be possibly a public call or something like that. Or there has been also instances that ISC had similar. So these 5 projects are like consortia projects, and they are conceived at the national level, and they are meant for those who already have expertise and can contribute to the aim that has been set for that project. However, there is also another scheme by which IISc had called for such proposals, and about 110 of them, and there were some verticals in that, like algorithm development, or there were, I don't remember the exact set of categories, but they were smaller projects of 1 or 2 year duration, and that's where the promising ones were given the funds what they needed. So if similar things they will be, if they come, maybe we can inform you, and then, but this will not happen before at least 1 year or 1.5 year, because the current ones are like sort of, the current mission is in sort of wrap up mode. So it will come only after maybe minimum of 1 year, or typically more than 1.5 year.
Okay, sir. Okay, sir. Sir, so maybe Sharad sir, I think we can keep in touch, and we can move forward. That's what I think right now. My area is fluid dynamics, and of course faculties are working in different areas. So I would like to take this further. Normally we write codes in Fortran and maybe Python. So we want to diversify. We want to bring in some advanced techniques. Yes.
Yeah, when we plan for the in-person workshop at an NIT Arunachal Pradesh, all of us who are here will probably come there as well. So then you can have a greater, I mean, all you as well as the other faculty members of NIT, if we can have,
yes, sir,
stronger interaction and discussion, as well as your students. Questions from the participants or any of the speakers? Okay, so then we hand it over to Dr. Vanav Kumar for his concluding remarks. I just wanted to share with everyone here that our speakers have kindly agreed to have the recording of this workshop posted online. So we will see how much of it we can post online. We will try to optimize it, and we will share the YouTube link with Dr. Vanav in NIT Arunachal Pradesh. So this will become available on Goa YouTube channel after whatever changes we need to make. So over to you, Dr. Vanav, for the concluding remarks.
Yes, sir. Yes, sir. Thank you, sir. Thank you for this wonderful workshop. So the idea actually came, not idea. So I was looking out for this CFD results. So my program used to hang always or divergence. It will get diverse. So I was searching and I dropped on this IIT Guwahati website. So the bigger picture, the bird's view was that IIT Goa was getting specialized in this high-end computing. So I thought that would be some use to me, and anyhow I dropped a email to Sharad sir. So he responded, and it went on, and we have done this workshop. So on that behalf, I am really thankful for Sharad sir, and of course, Director IIT Goa, MK Mishra sir, BK Mishra sir, and our Director Professor Pinkeshwar Mahanta sir, for taking out their time to come for the inaugural session, and of course the speakers. Ashish sir, Bharat sir, and Yogesh sir. So thank you very much for sparing your time on, of course, this Saturday. As we all know, Saturday is very important. Next week, again, week after week, we'll have the academic sessions. So sorry that we are not in person, and actually some snacks and these things are we are not able to arrange, but we hope to host you soon and receive the support in both teaching and academia. And of course, I like to thank all the participants who have participated during this workshop. So once again, I thank Sharad sir, and hope to continue this further. So thank you, sir. Of course, sir, not to say the least, the sponsoring agencies. So IIT Goa and National Supercomputing Mission. So thankful for them for arranging this. So on behalf of all our NIT fraternity, of course, our director, and on behalf of myself, I thank once again wholeheartedly to the whole team for their valuable time and valuable wisdom and knowledge. So thank you very much, sir.
Thank you, Dr. Vanav Kumar. Thank you, Ashish ji. Thank you, Bharat. Thank you, Sudhakar, for sparing time on a Saturday and rather at a short notice of 2 weeks. And thank you to all the participants who are here. And hopefully we will meet soon in NIT Arunachal Pradesh in a couple of months, and then we will have a more we will have a stronger workshop with hands-on exercises.
Yes. Thank you. Thank you.
Thank you, everyone. Take care. Bye-bye.
Bye.